En los instantes se ha podido ver un tren de satélites Starlink desde
Back in Boston, we didn't know what to do. So, she says, let's just wait it out. You know, we can be all poetic and just lose our minds together. Hey, wait. I wasn't alone. So, I'm still waiting for my turn. Hey, wait. Hey, wait.
A new satellite.
With some of these newer missions, we have let the community come up with their own ideas, their own way of implementing the mission, what their own science requirements are, and they bring their measurements to the table.
And ATREX had very good science, was very relevant to the kinds of questions we wanted answered, and its budget was reasonable and appropriate.
ATREX is an airborne campaign to try to understand how stratospheric water vapor affects climate.
It causes perhaps maybe 15 to 20% of the warming that we've had in the past 15 or 20 years.
So it turns out that small changes in the humidity of the stratosphere are very important for climate and important for surface temperature. They're actually comparable to the importance of greenhouse gases that everybody knows about.
So for example, we know that if you go back 30 years, carbon dioxide was less, quite a bit less 30 years ago. Methane was less quite a few, 30 years ago. Nitrous oxide was less 30 years ago. So we know these gases are increasing with time.
Gases that affect the chemistry of the stratosphere, which is where the ozone layer exists that protects us from ultraviolet radiation.
So understanding the rate at which this stuff gets into the stratosphere and how it changes is extremely important to looking at the climate of the stratosphere and how the stratosphere climate affects the lower atmosphere.
So we really need to understand what controls the humidity of the stratosphere and actually be able to predict that in the future in order to improve the accuracy of our predictions of future climate change. And it turns out the most important place to go sample to understand that is the tropical upper troposphere, the top of the troposphere in the tropics. It's called the tropopause, which is actually a very high altitude, which is why we need a high altitude aircraft to study it.
So the tropical tropopause is at about 55,000 feet in the tropics. So if you go down to the equator, you have to go up quite high, above 50,000 feet. And the tropical tropopause is really important to the global atmosphere because most of the gases that get into the stratosphere, all the air that's circulating upward into the stratosphere goes through this tropical tropopause region.
So that's basically a gateway to the stratosphere. The general circulation transports air upward in the tropics, goes into the stratosphere, and then is spread throughout the stratosphere and comes down at the higher latitudes in the polar region.
And this is what ATREX is focused on, to look at that motion of air into the stratosphere and how the water is removed from that air as it rises upward.
We know a lot about it, but there are some puzzles about the details of how the clouds are formed and under what conditions they form. So that's probably the most important thing that we hope to gain from ATREX.
ATREX will address a number of really important issues. It'll give us a better understanding of exchange between the troposphere and the stratosphere and how that impacts atmospheric composition, how that affects the chemistry that goes on in the upper atmosphere, and in the longer term, how that will affect the climate.
And that will help us to understand as we go forward trying to figure out what to do about climate change to better predict it and make better decisions.
How does the interaction between the upper troposphere and the lower stratosphere affect us down below? How are we going to find out? We have the questions. Now we'll be searching for the answers. Hawks' sense of hearing is excellent, and their eyesight the best in the entire animal world. Not only can they see greater distances than humans, but their visual acuity is 8 times that of ours. Yet we need to look even further, higher, deeper into the sky.
We live in the lowest layer of the atmosphere, which is the troposphere. The stratosphere is the next layer above us, so it's basically above altitudes of somewhere between 30 and 50,000 feet.
There are processes that take place in the stratosphere that have very direct impact on us.
So it's extremely important to understand the detailed process of water turning into clouds, those particles in clouds settling out. How does that detailed process occur, and then how will it change in the future?
What's been our big problem is getting the airplanes to the right place where they can make the measurements for long enough periods of time to do the observations.
So it turns out the Global Hawk is a perfect tool for sampling this part of the atmosphere. It's a high-altitude aircraft. It flies considerably higher than normal commercial aircraft, but it's also got this extremely long range.
So our bird here can climb to a cruise altitude of 65,000 feet and fly for up to 30 hours.
So we can basically, for example, we could fly from here to Australia in one flight.
So the basic geometry of the airplane, it has a wingspan of 116 feet, which is equivalent to the wingspan of a Boeing 737 transport aircraft, a length of about 65 feet, weighs about 27,000 pounds, fully fueled at takeoff.
In comparison, in the past, people have used manned high-altitude aircraft like the ER-2 or the WB-57. However, those have very short range.
Now that we have the Global Hawks, they have a much longer flight duration. They can get to these key areas to appropriately attack the science questions that we've been thinking about for a very long time now.
Basically, for this program, we searched out the best instrumentation, the best expertise in making these measurements, and invited them to be part of the program for the proposal for the ATREX mission.
Once the major science campaign, the project mission scientist selects the instrument teams, that's really when our work gets started. We will then visit them and begin coordinating all the mechanical and electrical interfaces we need to do to get them mounted on the airplane.
You have to determine everything from the size of the instrument, so you know how much space it's going to occupy or needs to occupy in the aircraft, how much the instrument weighs, so you can be sure that what you design mechanically for installing the instrument on the aircraft is of sufficient strength to be able to hold the instrument in the aircraft.
In some cases, you'll see probes sticking out of the airplane, so all of that has to go through aerodynamic analysis, etc. Structural mounts inside have to be properly stress analyzed, so we make sure all that happens. So we coordinate with all the proper technical fields to get ready for the instrument to arrive here.
From the time we first start communicating with the instruments teams until we're ready to actually start performing science with all the instruments on the aircraft, it takes about a year and a half of really hard work, close coordination, and a lot of good communication between everybody.
We're using state-of-the-art instruments, or cutting-edge instruments, to measure things like water vapor, clouds, and temperature, and a whole bunch of trace gases.
We have a very sophisticated instrument called the Cloud Physics LiDAR. It's a laser, shoots out the bottom of the nose of the plane, and as the laser goes down, some of the light gets scattered back, and there's a telescope that collects that light. And because you know how long it takes the light to go down and then come back up, you can tell what kind of cloud structure there is below the plane. So if we see very thin clouds, this laser can detect those very thin clouds. We have a meteorological system on board the plane that measures winds, temperatures, and pressure. And it's a best meteorological instrument in the world for measuring these. Imagine how hard it is to measure from a plane that is going a few hundred miles per hour. So it's a really hard measurement to make, and they do it. We have water vapor measurements, 2 water vapor measurements on board the plane. Water vapor is important to look at how air that's going into the stratosphere gets freeze-dried, so you have to have a really high-quality water vapor measurement, and we have 2 instruments to do that. We measure ozone on board this plane. Ozone, as I mentioned, the ozone layer screens ultraviolet radiation, so we have to know what the ozone looks like. There's actually very little ozone in the lower atmosphere, and there's a lot as you get into the stratosphere. So we use ozone actually to tell us the difference between stratospheric air and tropospheric air. We have another instrument that actually sucks little gas samples, has little cans, so it'll suck in a little air, and then you bring those cans back, take them to a lab, and you can literally measure 100 different gases from these little gas sample cans. And that's really important because you can look at all sorts of natural and human-produced gases to look at things like ozone depletion and climate change.
So all of these will tell us how air is transported through the tropical tropopause region and how it's dried to the very dry conditions of the stratosphere.
ATREX is sort of a pathfinder in terms of investigating some of these processes. And when I say pathfinder, it's utilizing a brand new tool, and that is the Global Hawk.
This is a hybrid. It's like a satellite that you control from a control room, like a mission control, but it has nobody in it, like a satellite. So it's really a new and revolutionary way of doing science.
With the science that we do at NASA, we need to combine the satellite data with aircraft data, with modeling data, and even some measurements from the ground all together to answer the science questions the right way.
In 50 years, we'll look back on this plane, and it'll be very common, it'll be used all over the world. I really believe that planes like the Global Hawk are going to change atmospheric science in a very profound way, and for the betterment of everybody who lives here on the Earth.
Everything is ready. We should be airborne soon.
On a remote peninsula in the South Pacific, a rocket and 10 small satellites are about to launch a new era in spaceflight. Rocket Lab's Electron rocket is a new player in the space arena, and those tiny spacecraft, called CubeSats, represent big dreams.
It's kind of like the preeminent, most exciting mission within the whole company. The whole team is just incredibly excited to have that NASA logo on the side of the vehicle and fly those payloads.
The NASA payload about to launch on the Electron rocket is called ELANA 19. ELANA stands for Educational Launch of Nanosatellites, part of NASA's CubeSat launch initiative. This is the agency's way of providing a path to space for CubeSats, compact satellites that pack a lot of science into a package about the size of a loaf of bread.
Space is no longer just for high-value science or the intelligence community. It is a place for a payload that you can create that can get up to space.
Until now, CubeSats have always launched with larger spacecraft, but flying as a hitchhiker limited where they could go and the science they could do. That's what makes this Rocket Lab flight so historic. It's the first time these small satellites are the stars of their own show, flying on a rocket designed for their needs. The 10 CubeSats flying on ELANA 19 were developed by teams from across the nation, from high schools and universities to NASA field centers. Da Vinci was developed by a student-led team at North Idaho STEM Charter Academy. It's designed to connect to students around the world by broadcasting education-related messages through amateur radio in Morse code. It also carries a Globalstar modem and Arducan, allowing users to upload digital messages or see photos of Earth from orbit.
I don't know if anyone remembers like the Ovaltine messages and stuff on the radio way back when, but our goal is to do something like that where they have to tune in every week or every other week to get this new message and decode it and really dive into that information so that they develop an interest in space and they say, oh, hey, I can communicate with something that's not even on this planet.
RSAT was developed by a team of midshipmen from the U.S. Naval Academy in Annapolis, Maryland. This crab-like CubeSat has a pair of robotic arms designed to grab a host satellite and maneuver around it to take photos, or potentially even make repairs if a spacecraft isn't working properly. The CubeSat STF-1, or Simulation to Flight 1, is a collaboration between NASA Independent Verification and Validation Program with West Virginia University and small businesses. STF-1 will monitor space weather over Earth's poles and test the durability of new materials for use in LEDs. But it's also designed to demonstrate a simulation and test platform to aid in the development of future CubeSat missions. These CubeSats show that small satellites have an important and growing role in space exploration. NASA's Venture-class launch service was created in 2015 to provide CubeSats their own ride to space, expanding launch and science opportunities for small satellites and sparking a brand new segment of the space launch industry. Rocket Lab's Electron rocket is one of 2 vehicles NASA selected for Venture-class missions. It's smaller and lighter than other launchers in NASA's stable, but that's the whole point.
The intent is for the Venture-class launches to occur at a rapid pace that match the iteration and design cycle that CubeSats can go through. So instead of having a launch for a primary mission once every 2 years, once every 5 years, the real goal is to see Venture-class rockets get to a cadence where they can see regular access to orbit.
Many of the CubeSats on the Alana 19 mission are designed to benefit future missions. Shields 1 was developed by NASA's Langley Research Center in Hampton, Virginia. Its objective? To test materials that could be used to shield spacecraft against radiation.
This is a radiation effects experiment where we're looking at the performance of the materials and the electronics, and it would have a potentially large impact for improving performance of future spacecraft.
NMTSat was built by approximately 50 undergraduate and graduate students, primarily from New Mexico Tech in Albuquerque, New Mexico. It's designed to use onboard sensors to collect data on Earth's magnetic field, take atmospheric weather measurements, and carry out an optical beacon experiment. The next spacecraft was developed by teams on opposite sides of the country, in Florida and California. It's called CHOMPT, which stands for CubeSat Handling of Multi-System Precision Time Transfer. This mission is a collaboration between the University of Florida in Gainesville and NASA's Ames Research Center in Mountain View, California. CHOMPT uses lasers instead of radio waves to demonstrate new ways to navigate and network satellites in deep space. The Advanced Electrical Bus, or ALBUS, was developed by NASA's Glenn Research Center in Cleveland, Ohio. ALBUS will demonstrate shape memory alloy mechanisms for deployable solar arrays. It'll also serve as a pathfinder for high power density CubeSats.
The shape memory alloys themselves are really good technology because they are low mass, they can produce low shock, and we can reset them. So we can actually reset our mechanisms to test it again to deploy to make sure we're going to have a successful mission.
While the CubeSats are prepared for flight, their ride, the Electron rocket, begins to take shape. Fully assembled, the Electron stands nearly 56 feet tall, a smaller rocket dedicated to launching small payloads. It's a 3-stage carbon composite vehicle, topped by a payload fairing to protect the CubeSats during launch. The Electron's engines and avionics are manufactured here in the United States at Rocket Lab's facility in Huntington Beach, California. In fact, the company's Rutherford engine is the first ever oxygen kerosene rocket engine built using 3D printed main components. Then they're sent to Rocket Lab's facility in Auckland, New Zealand. Here, the company puts its engines to the test before final integration. It's also where Rocket Lab manufactures the vehicle's stages and payload fairing. But until the rocket is assembled and tested in New Zealand, the CubeSats will wait in California. It will all come together when the spacecraft arrive from Huntington Beach just a few weeks before launch. CubeSail was built by the University of Illinois at Urbana-Champaign in CU Aerospace. It carries a 250-meter solar sail ribbon, technology that's being evaluated for use on future spacecraft, such as scientific missions to interstellar space.
CubeSail is going to be doing a technology demonstration of the deployment technique as a stepping stone toward even larger missions we have planned on the road, like iSail and UltraSail.
The ISX CubeSat, or Ionospheric Scintillation Explorer, is a collaboration between SRI International and Polysat at Cal Poly San Luis Obispo, California. ISX is designed to take a closer look at plasma fluctuations in the upper atmosphere and learn more about how they affect radio communications with satellites. Up next is Ceres, the CubeSat Compact Radiation Belt Explorer. It was developed by NASA's Goddard Space Flight Center in Greenbelt, Maryland. Ceres will fly into Earth's Van Allen radiation belts to study the high-energy particles streaming toward the Earth from the Sun and learn more about how electrons in the radiation belts are energized and lost.
CubeSats go into the clean room and they do their standalone processing. So that's any sort of checkouts, charging. Basically, they're getting ready to get into that final package, the dispenser. That's the piece of hardware that's actually going to launch them out into space off of the rocket.
November 2018. With the Electron rocket ready for final integration and launch, the CubeSats are shipped from California all the way to Auckland, New Zealand. But the Electron rocket elements and all the Elana 19 CubeSats still have to make one more journey on Earth. It takes a caravan of trucks about 8 hours to make the 575-kilometer journey from Auckland to Rocket Lab's Launch Complex 1 at Mahia Peninsula on the island's east coast. But this remote launch site is worth the drive.
So from one single launch site, we can launch all the way to 39 degrees inclination, that's due east, all the way up to sun synchronous, which is about 98 degrees depending on the altitude. So that's the widest range of inclinations available from any launch site in the world.
On the ground at the Mahia Launch Complex, the rocket stages are carefully brought together and inspected to ensure everything is perfect. The CubeSats are installed on the Electron payload plate, the interface between the rocket and the satellites. Then Elana 19 is encapsulated inside the Electron rocket's payload fairing, where the CubeSats will stay until they're in space. The entire rocket is manually rolled out to the launch pad for a rehearsal of the launch day that's quickly approaching. Liftoff is planned for December 12, 2018, and the vehicle is ready. But dangerously strong winds keep the Electron on the ground for 4 more days. Their fortunes change on December 16th, when the winds aloft finally go green.
5, 4, 3, 2.
The Electron rocket's 9 Rutherford engines ignite, and history is made. Less than an hour into the flight, the Elana 19 CubeSats are released. Instead of hitching a ride, these small spacecraft have a dedicated ride that can deploy each one to just the right orbit for maximum science. Elana gives students and teachers a low-cost pathway to space to test new technologies, make new discoveries, and create new connections to each other and the future. Small satellites, big dreams, and even bigger potential for future CubeSats needing a Venture-class ride into space. To launch with Elana, visit nasa.gov/Elana.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
STEM fans, are you ready? Let's hear it for the world-class NASA STEM Stars team. From NASA centers across the country, we present Doug Hoffman.
Good afternoon and welcome to another episode of NASA STEM Stars. I'm Jen Hudgens from the Kennedy Space Center, and today we have Doug Hoffman from JPL. So welcome today, Doug.
I'm well, thanks for hosting me.
Yeah, absolutely. So this 30 minutes is going to go by really fast. So like I just told our viewers, we're going to do a little deep dive into your career out at JPL. But before we get to that, can you tell us a little bit about your background, where you grew up, maybe some of your education?
Sure. So I'm from Santa Rosa, California, originally born in San Francisco, grew up in the Bay Area, and I went to Santa Rosa Junior College for my first 2 years of college, and then transferred to UC San Diego for my bachelor's and master's degree in mechanical engineering, and then on to Caltech, the California Institute of Technology in Pasadena for another master's degree and for my PhD.
So I see some pictures there. It looks like you were wearing a basketball uniform, and there's one of you playing tennis. So were those interests of yours in high school?
Yeah, I came from kind of a non-traditional STEM background in that I was an athlete. Although I did play basketball in high school, mostly I was a standout tennis player. So, I went on to play tennis in junior college at Santa Rosa Junior College, and then later for the NCAA at UC San Diego. So I come to NASA from the NCAA athletics background, which is sort of a non-conventional path to end up at NASA.
Well, that might be really helpful for students to know, because there are some great athletes out there that are also pursuing, STEM degrees, and that might be a bit of an encouragement for students out there. So thanks for sharing that non-traditional type background and path into NASA. Did you have any other interests in high school?
Yeah, I mean, mostly in high school, I was known for being an artist. I didn't take any honors or AP classes except for AP Art and AP Spanish. I actually got a 5 on the AP Art exam, which I'm told is quite difficult. So, I really had set up for a career in art as opposed to a career in science and engineering. I only made the switch into science and engineering once I was already in college, and it looked like a more employable route for the future.
That is an amazing piece of art there. And tell us a little bit about this picture here.
So I went to a brand new high school, Maria Carrillo High School in Santa Rosa, California. When I was in middle school, they had a contest to draw the mascot for the high school. So I won that contest as a 9th grader or 10th grader. And then the new principal of the high school put the mascot into marble on the gym floor. So it's been 20 years plus since I graduated from high school, but the mascot that I drew as a 15-year-old is still on the floor of the gymnasium at the high school. So that's really cool to have. And my high school is now known for having a famous Olympic athlete at it, Maya Dorado, who competed in the Rio Olympics and won many gold medals, is a graduate of my high school as well.
Wow, that's probably very cool to still be able to say that. Do you think your kids are going to be able to visit that and see that someday, or do you live close by still?
I don't live that close anymore. I live in Southern California now, near Pasadena, where the Jet Propulsion Laboratory is. But Northern California is, a 7-hour drive away, and I have deep roots there. So
that's awesome. So tell me, did you have any mentors in high school? I know you mentioned that you were going to be going into art when you started pursuing your bachelor's, but when you got to college, did you have any mentors that may have pushed you towards a STEM degree, or what made you make that switch?
Yeah, so that switch happened for me, kind of my freshman year where I was attending junior college. I had straight A's in high school, but I wasn't, doing any honors classes or AP classes in sort of STEM fields. So it was sort of a discussion, with some family members, my mom, where, I was advised that if I was good at math, I should probably go into engineering as opposed to going into art, just because it seemed more employable. So for me, I just kind of arbitrarily signed up for engineering classes my first semester in junior college, and signed up for the engineering track, which ultimately resulted in my AS degree in engineering. And then that was kind of the pathway to transferring to UC San Diego, where I got into the mechanical engineering department. So it was not a traditional route where a lot of students are doing robotics and STEM as very young ages, doing math bowl competitions and so on. I did not come from that kind of background. I came into science and engineering as an adult, which is, again, not traditional.
Yeah, so you had a lot to learn getting going from the bottom. So I would think, though, as an adult, you probably learned a little bit easier because you're a little more dedicated than maybe as a high school student, being shown all these different sciences where you had your track, like that picture we just saw, where you get really hands-on practice in a true lab, and then, realize which part of engineering that you liked.
Yeah, I have to hand it to, Santa Rosa Junior College and UC San Diego and Caltech. They really molded me into a scientist and engineer pretty much from a blank canvas. So that's why the colleges are there and why they have rigorous academic programs. So I do have some blind sides as a NASA scientist. I'm not as good with CAD software and robotics programming as many other engineers, and that's because I just didn't grow up doing those kinds of things. So I'm much more of a scientist than I am an engineer because of that.
Yeah, I get that. Like Excel came out after I had graduated from college, so it's something I had to learn, further down the road. So I'm sure everybody would understand that story in some aspect or another. So, and I think you brought one of your graduation pictures from college to show us, so we'll put that up. And that was University of California in San Diego. Is that what you said?
Yeah, yes. That's right. That's my graduation from UCSD with my bachelor's degree, and then I got my master's degree the year after. So going to school in La Jolla in Southern California, down near San Diego, was one of the highlights of my life. That was an amazing school. I spent, like I said, a lot of my time playing NCAA tennis and surfing. So it was a really wonderful experience.
And then you jumped right into your master's from your bachelor's. Is that what you just said?
Yeah, there's a program called an MSBS program where they allow you to take graduate classes in lieu of electives as a senior undergrad. And then
nice.
1 year later, you can take a full load of graduate classes and then write a thesis, and you can get your master's degree in 5 years instead of the typical 6 years that it would normally take from the start of your undergrad degree. So it was a nice year to add a master's degree in mechanical engineering. But then I transferred to Caltech and started over again with a master's degree and a PhD in a different field of material science, which is what I do at NASA now. So I have a set of degrees in mechanical engineering that makes me a mechanical engineer, but I am not a mechanical engineer anymore.
That's great. So before we jump into what you actually do out at the Jet Propulsion Laboratory, we're going to take a little break here for a brand new segment that we've started called the Lightning Round, where it's a segment where I'm going to ask you some rapid fire questions, and you have 30 seconds to respond with a one-word answer. And we're going to see how many questions we can get you through. So are you ready for the Lightning Round, Doug?
Hit me.
All right.
Time for NASA STEM Stars Lightning Round.
All right, so if we can put up the leaderboard from last week and we can see how many questions we need you to beat, get you up. Okay, so we need to at least get maybe 9. Let's try for 9 today. What do you think? All right, so let's put 30 seconds up on the clock and we'll go ahead and get started. Tennis shoes or flip-flops?
Tennis shoes.
Star Trek or Star Wars?
Star Wars.
Homework or yard work?
Yard work.
Pen or pencil?
Pen.
Hero or villain?
Villain.
City or country?
City.
TV shows or movies?
Movies.
Tie-dye or bow tie?
Bow tie.
Introvert or extrovert?
Introvert.
All right, you got 10 questions. You answered 10 questions, and you said introvert. I can't believe
my
that.
wife is probably going to listen to this and be like, what did you say?
And I love that you said villain over hero, because I'm of the persuasion that you can't have a good story without a villain. So who's your favorite villain?
Well, I've got the Lex Luthor, shaved head book. So.
That's great. All right, Lex Luthor and Superman. Mine is Maleficent from
just watched
Sleeping
that
Beauty.
Sleeping Beauty
Yes.
with my.
Yes.
I just watched that with my daughters, and she is delightfully villainous.
Yes, you cannot have a good story without a good villain. So I agree with you there. So, all right. So we got you on the leaderboard. So you lead with 10 questions. So if everybody that's watching today will give us a thumbs up in the chat and congratulate Doug for doing that so well. And we're going to jump right in now to what you're doing at JPL. Can you share with us? You said you're a materials engineer or a scientist. So tell us, what does that mean?
So I work at JPL in the Materials Development and Manufacturing Technology Group, which is a group that I co-founded with a couple of colleagues a number of years ago. And what you see in this picture is the lab that I founded, which is called the JPL Metallurgy Lab. So this is a lab dedicated to the invention of new metal alloys and manufacturing technologies necessary to make spacecraft survive in extreme environments. So it's a lab specifically dedicated to addressing the concerns that we have at NASA about going to different planets or being in deep space, being in high radiation environments, cold environments, hot environments in the case of Venus, and then trying to develop new materials that will be able to more easily handle those conditions than conventional materials. So that is the lab that we work on, and we've got quite a big group of scientists and engineers that work in this effort. More than 20 scientists and engineers that work in this materials and manufacturing effort at NASA JPL. So we do everything from metal 3D printing to machining and casting and injection molding and invention of new alloys. So the best way I like to describe what I do is I'm an inventor. I invent new materials and new manufacturing techniques for making materials so that we can make spacecraft better.
So you mentioned spacecraft. Have you done any work with the rovers? Because I know down at JPL, that's what most of what they're known for is Curiosity, Perseverance, Ingenuity. Have you had a chance to see the rovers or help develop anything that those rovers are built with?
Yeah, the first rover, Curiosity, launched the month after I was hired in JPL back in 2010. So I didn't have a lot of opportunity to work on those other than consulting on some last-minute manufacturing problems. And then Perseverance, we worked on it in more detail. I think the highlight of the effort from our larger group on Perseverance was that we have 11 3D printed metal parts that are on the Perseverance rover. So back when Curiosity launched, we had no capacity for metal 3D printing. And now with Perseverance, we've got some critical parts on 2 different instruments. One is called Pixel and one is called Moxie that have 3D printed metal parts in them. So that's a big achievement from our effort, even though I played only a small role in the fabrication of those parts.
Yeah, we actually had a question from a student. Amani wanted to know, have you made alloys from asteroid materials.
Yeah, so that's called in situ resource utilization, or ISRU, and we have not done that yet. Clearly, the easier material to get is from the moon or from Mars. Asteroids are difficult to land on or capture. But yeah, NASA's been working for many years on trying to take regolith, which is the dirt from planetary bodies, and then try to manufacture with it. I know there's an experiment that's going to be on the space station that just launched yesterday, which will be an experiment to 3D print regolith simulant on a 3D printer on the space station that was built by a company called Redwire that is going to be up there soon. So that's some exciting work to look forward to in the future.
That's great. And another student also wanted to know, do you use a 3D printer in your lab? So I think you kind of answered that, but I'll go ahead and throw that ball into your court.
Yeah. We have 3D printer in our lab, but we also have the JPL Additive Manufacturing Center. And additive manufacturing is just a fancy name for 3D printing, but we've got several metal 3D printers here at JPL that produce aluminum and titanium, and then we use the printers to develop new materials, like materials where we blend between multiple materials together in a single part. And then we also have a very large plastics 3D printing lab. Most people don't know, but we can also 3D print plastics for spacecraft as well, if they're the right kind of plastics. So yes, we do a lot of 3D printing at JPL.
And they also wanted to know, they said that's cool. So you've used regolith in 3D printing, so in your lab particularly, or you just have seen it done?
That's not in my lab, but there is another lab at JPL where they're looking at sintering together regolith to make structures out of. But most of that work goes on at other NASA centers, like Johnson Space Center, not at JPL. My radar really until I was at UCSD, and one of the professors at UCSD was Dr. Sally Ride, a very famous U.S. astronaut, and so I started. I recall actually I had a seminar at UCSD by astronaut Greg Lintieres, and that got me really thinking, like, wow, this would be really fun to work at NASA. So when I decided to go to grad school, I specifically sought out opportunities at Caltech and at MIT that were affiliated with NASA. And ultimately, I went to Caltech because of the proximity.
Well, it sounds like you and I have something in common, because I've had the benefit of meeting Sally Ride too, and she was my inspiration. So who knew? Who knew?
Yeah, fantastic. I remember. Oh, sorry, go ahead.
No, go ahead. You remember what?
I was just going to say that my dad applied for the teacher in space astronaut job back from the 1980s. So I'm still old enough to remember Kristen McAuliffe, who was the first teacher that was going to go to space and teach from the space shuttle from the Challenger mission. So that's how old I am. In fact, the space shuttle flew the first time the year I was born. And then it stopped flying the day my son was born. I had launch tickets for the last launch of I guess Endeavour, and my son was born that day. Between my birth and the birth of my first son was bracketed.
We had a question from a student that wanted to know a little bit more about metallic glass and whether or not that's similar to silica.
So silica is oxide glass, and the atoms are different, the bonds different. So you can go to Google to look at metallic glass, but it looks like metal. It just has the structure of like a window pane glass, for example. So not all glasses are transparent. Like obsidian is a black volcanic glass that you may be familiar with. Metallic glass is made of elements like titanium and zirconium and copper and aluminum, and it looks like glass, but the atoms are all arranged randomly. So it looks like a metal, but it has the structure of a glass. It's sort of a nuance.
And it seemed like when you were explaining that project, the benefits of using metallic glass was because it can withstand colder climates. Is that correct, or is there other benefits to it?
Yeah, it has a lot of benefits, but one is that it has very good wear resistance at cold temperatures. So when you make gearboxes out of metallic glass, they can operate in cold environments without having to be lubricated by, like liquid lubricants that we have to use on the Mars rover, for example. So it's a way to make gearboxes that are dry, as we call them.
Gotcha. Another question, did you do any internships during college?
And that's a great question, and the answer is no. As I mentioned before, I came from the NCAA world, so I was an athlete. So to play NCAA sports, it's a full-time commitment. So I was doing, two different tennis sessions a day, most of the year, and then that didn't leave a lot of time outside of school to do internships when you're an athlete. So I didn't have the opportunity to do any internships. And then when I was at Caltech, I played semi-professional tennis, so that also made it difficult to do any internships. So mostly I got my hands-on work done while an undergrad in the labs, and then later as a graduate student at Caltech, where my 4 years of graduate school was in the lab, building things. So it's, again, a not conventional background to not have done a lot of internships. But for all the athletes out there who think that, you need to be able to do internships to be able to get into NASA, it's not necessarily true. You can be an athlete and still do a career in STEM.
That is great advice, and I hope that we have some athletes watching today that will take your words to heart. So can you tell us what is your favorite part about working at NASA at JPL? What are some awesome things about your job? What have you got to do that's been cool?
Oh my gosh, it's just amazing. Well, I guess I should also apologize for the audio. For some reason, we get some lagging here because we're doing these things remotely, as always. The diversity of the things I work on at JPL, one day I'm working on building a 3D printed excavating tool to cut through ices, which we might experience on the moon of Jupiter, Europa. The next day, I'm doing hypervelocity impact testing, simulating debris impacts on a space vehicle. The next day, I'm doing gearboxes for a rover. So you really, never know what you're going to be working on from one day to the next. And the diversity of things you get to work on is so amazing. It's just never dull here here at JPL, and that's very exciting. We also get to have a lot of collaborations with outside institutions and even commercial companies that makes working here really fun. But also the thing that I really enjoy is that I get to do events like this. You can tell that what we do is so exciting to the public that students are willing to sign on and listen to people like me talk about building spacecraft. So the public engagement, that really is what makes it worthwhile. Knowing that what we're doing is appreciated by the public, that makes it really special.
I bet you've met some pretty famous people along the way as well, haven't you?
Yes, I have a collection of pictures of astronauts that have visited my lab. So I've got a dozen or more pictures of myself with astronauts that have come by and visited. When they come by and visit JPL, they'll often go around and see some of the labs, which is fun. And yes, other high-profile people that have visited lab or where we've gone and visited lab. I think my best experience was when I met President Obama back in 2014 when I won the Presidential Early Career Award. And got to go to the White House. And it was not just amazing to meet the president, but I also got to meet the director, the administrator of NASA, General Charlie Bolden, who flew the space shuttle. And he was on the stick of the space shuttle when the Hubble Space Telescope was put into orbit. And so I got to meet him, and his office made a cake for me and the other award winners from NASA, which was a surreal experience. And then later I got to go over to the White House, which you see in that picture. And President Obama was so gracious to us. It was just, one of the most amazing days ever to go meet those two phenomenal men.
That is so amazing and inspiring. And I'm sure you were inspired as well just by meeting them. So thank you for sharing that. We just have a couple minutes left. So I want to give the floor back to you if you have any last minute words of advice for the students that may be watching and maybe floundering with ideas for their future careers.
Yeah. So I guess a couple, words of wisdom. I don't presume to know the ages of the people who are watching this or who will be watching this. But there are many non-conventional ways to get into NASA, even from art and design background. We have many people at JPL and in NASA who are from, art and design, architecture kinds of backgrounds, and they make amazing contributions. We've got many athletes and then many people from very rigorous STEM backgrounds. So, whatever your passion is, there's likely a home for you at NASA or in space exploration with commercial companies. So you have lots of opportunities. So don't feel like you need to, satisfy all these requirements to be able to stamp the check to get into NASA. You can get to NASA from many different ways, including through community college and then transferring to a university, playing tennis, not doing any internships, and still being able to get into NASA. And then as far as the academics, my biggest advice to students always is to not lose focus when you start college. So many students think that the ultimate prize is being successful in high school and getting into that top-notch college, and then they sort of let off the gas pedal when they get into college and let their grades slip. And it becomes difficult to recover from that in your upper division classes later. So my biggest advice is to make sure you continue focus. The most important part of your career in STEM starts the day of your freshman year of college, and everything that happened before in high school is washed away, and you start fresh again in college. So you need to keep that in mind and keep the pedal to the metal with your homework and schooling, and make sure that you give your best effort starting then.
That is all brilliant advice. So thank you, Doug, for sharing that with us and for sharing your day with us as well. Just a quick challenge to our students. I want to tell you all about a heat shield activity where you can actually build your own heat shield and be a material scientist like Doug. We're going to drop that link in the chat so you can go check out that activity, and make sure you share your work with us at #NextGenSTEM. And make sure you also subscribe to NASA STEM Stars so you don't miss an episode in the future. And then next week's episode, we're going to be with George Jarosby, who works with the Diagnostics and Prognostics group at Ames. And that'll be next Wednesday at 2 p.m. Eastern. So that is all that we have for today. Again, thank you so much, Doug, for joining us. And I want to encourage our STEM fans to keep their foot to that pedal and we'll see you again next week. Thanks for joining us.
We went to 5 meters altitude, and then we translated out, but unlike every other flight where we gone out, we didn't come back again. This is about where we landed, and prior to that, we can see that we went to 10 meters altitude, and then came down again. So that looks great, and so we're right in the vicinity of where we wanted to be.
One of our missions at NASA is to protect our planet and maintain the beauty that we call Earth. Hi, I'm Jackie Quinn. I look for clean water on Earth and on the Moon. And we call it MSOLO, which is Mass Spec Observing Lunar Operations, to go out and look for these resources that could actually enable us to sustain human exploration on the lunar surface, and then it says that stepping stone to get us on to Mars. I love to be outside. I made the film crew come out here. The Earth is pretty cool, and if you can capture that energy and bring it back into your workplace, it just makes you all the better and more creative. That's why it's so important to protect every bit of it. I've had an opportunity to work on a number of environmental cleanup technologies, actually going out and doing the cleanup at the sites. I've worked on the space shuttle, and then I went into technology development, and now I'm working on a lunar mission. I mean, what a cool way to grow up, right? Professionally.
One of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
Welcome to the Jet Propulsion Laboratory, a NASA facility here in Southern California that specializes in the robotic exploration of Earth and space. I'm Marina Jurica, and we are very excited up here in the viewing gallery of the Space Assembly Building. And down below, you can see NISAR, and it is in the clean room below us, the next Earth observing satellite, which stands for NASA, ISRO, the Indian Space Research Organization we are teaming up with for this mission, Synthetic Aperture Radar. You can join in on the conversation here live by putting your questions in the comments. Here to break down how this satellite will give us a unique view of the Earth is NISAR's project scientist, Paul Rosen. And a little later in the conversation, we're going to talk about all the cool new technology on board this satellite with instrument manager Wendy Edelstein. Good afternoon, Paul.
Hi, Marina. Hi, everybody.
So you guys had a very special delivery just a couple of days ago. Can you tell me about the new hardware that was just delivered and pointed out to me?
Yeah, we sure did. We got the S-band instrument from ISRO. It's in the silver covering over there in the corner. So it looks kind of small, but it's a very, very important instrument. It will marry together with our L-band instrument and put a 2-frequency radar in space.
Now, tell me a little bit about what sets NISAR apart from other Earth satellites that are in orbit right now.
It's unique in almost every single way. It combines many different things, different techniques, and different modes. So we have 2 radars, one from the US, one from India. They're 2 different frequencies. So we can make color radar images of the Earth, which is unique. It also has polarimetric capability, which is a fancy way of saying that it has radar Polaroid glasses, which allows us to see the Earth in a particular way, which is unique also. There's many, many other features as well. It strobes the Earth, measures the Earth every 12 days repeatedly over the life of the mission at high resolution and high temporal sampling, which allows us to make movies of the Earth effectively using this color Polaroid system. It's very, very, very cool.
It is very cool. And talking about how it works right now, we're going to be answering your social media questions live. Just pop it in the comment box. And we already have one from Charles on Facebook asking, will the radar accurately see the surface of the Earth? And is it like a heat tray? Microwaves bonking me on the head sound dangerous to me.
Yeah, we will certainly make accurate measurements. This is designed specifically for accuracy in measuring very small motions of the Earth. As far as bonking you on the head with microwaves, it is a microwave instrument, but the amount of energy compared to your microwave oven is so tiny, it just melds in with the light and all the other radiation like your cell phone and everything else. So it's absolutely nothing to worry about. We're a million meters in space, so the amount of power we transmit is very, very small by the time it gets to the Earth.
And that space is a good thing.
Yes, yes, yes.
Now, NISAR is going to open our eyes to a potential of seeing the ground in many places that we haven't been able to see before. It's being called an all-weather satellite. Can you tell me what that means?
Yeah, well, by virtue of the radar wavelength, which is about this long, it's not sensitive to raindrops or cloud particles in any way. So we actually just penetrate right through that, unlike optical lights, and bounce off the ground. It comes back through the clouds, and we can see it. So it doesn't matter whether it's raining or cloudy, we can see right through it. So it's all weather in that sense. We also have our own source of light. We generate the energy, transmit it, so it doesn't rely on sunlight. So in that sense, we're also day and night and all weather. So it's very, very powerful. We have reliable measurements at all times.
Day, night, no matter what kind of weather, and 24/7. Sounds like it's going to be working hard.
Oh, yeah. As will we, looking at the data.
Yes. Now, with the ability to see through anything, how will that help people deal with natural disasters like volcanoes or landslides?
Well, we take these data and we model them. We try to understand the physics of the Earth, and we can then take that knowledge from understanding the physics of the Earth and predict potentially how volcanoes will erupt. We can also monitor the motion of the Earth and see if it's starting to move before an eruption actually occurs, which then allows people to respond. They can evacuate if necessary, or just take other mitigation steps.
And early warnings are such a key when it helps those people during natural disaster events.
Absolutely, yeah.
Now, this is an incredible amount of data coming down. We've talked about this. It is just hard for me to even wrap my head around it. Can you make us understand how large a petabyte of data is?
Yeah, I was thinking about this. I've thought about this a lot, actually. You can think of it as something like 200,000 DVDs. So a DVD contains a movie, which a movie might be around 2 hours. So like 400,000 hours worth of movies, which if you were watching 24/7 would take you 45 years to get through. So it's a lot of data. Of course, we're not going to take 45 years to look at it. We use very fast computers to analyze it and reduce that data down to the scientific results that we're interested in.
But you will still be busy nonetheless.
Oh, yeah. Yeah.
Excited, but busy.
Yes.
All right, our next question from social media comes from Hari Raj on Twitter, asking, can NISAR detect a volcanic eruption before it happens?
Yeah, so that's what I was saying earlier. We can monitor the motion of the ground down to a fraction of an inch as it's moving. So if there is pre-eruptive behavior, as they call it, then yes, we can see it inflating or deflating, moving around on the ground, and predict whether it will erupt or not.
And our next question from Greg on Facebook asking, is it similar to LIDAR?
It is similar to LIDAR in the sense that a LIDAR is an active sensor, meaning it generates its own source of energy. It transmits a pulse of some sort. It goes to the object it's interested in, bounces off, and then receives that signal. So it's the same process. LiDAR uses optical wavelengths or near optical wavelengths, which are very, very tiny. They're in the micron range. Whereas for radar, we're looking at wavelengths that are quite a bit longer. So we're sensitive to entirely different things.
That's really fascinating. And I briefly mentioned this earlier, but you partnered with ISRO to make this satellite. Can you tell me a little bit about why NASA chose to internationally collaborate?
Well, international collaborations are extremely important for a variety of reasons. All of the spacefaring nations, and other nations for that matter, are interested in the same kinds of things from a scientific and an applications point of view. We care about the Earth. We care about our people. We want to understand the Earth so that we can properly steward our resources and all the people that are in our countries. So ISRO and NASA share that common desire, and we know that radar is a very, very useful scientific tool for doing this. We each had our own ideas about putting radars in space. By collaborating, we can create a system that's even more powerful than any one nation could do by itself or could afford by itself. So it really helps share resources towards a common goal.
And what's incredible is that space really knows no boundaries.
That's absolutely true in many ways.
All right, now Wim on Facebook asks, what kind of ground stations will be in charge of downlinking all that data?
Okay, so we have I think 3 or 4 different locations where we're downlinking the data. We have, by the way, an extremely high rate downlink system specially designed for this mission. For those who care about the numbers, it's on the order of 4 gigabits per second downlink, which is several orders of magnitude more than NASA has done before. The ground stations are located mostly in the north. There's some in Svalbard, which is north of Norway, and another one at the Alaska Satellite Facility in Alaska, in Fairbanks. We have a couple of others, one in Wallops in the United States and one in the southern tip of South America. So even with the very high data rate, we need many different stations to be able to observe and downlink data continuously because of the high data volume.
Well, this all sounds really great, Paul. What are your next milestones that your team wants to make as we move forward?
Well, we are integrating the 2 radars together. The one that just arrived, we're going to be testing it by itself and then integrating it together. I think you're going to hear more about that later. And then the major milestone is testing them together and then eventually delivering it back to India to be integrated with the spacecraft. That's the immediate goal that we're looking at.
And we're looking at a launch date of next year.
Yeah, it's towards the end of next year. That's correct.
So a lot of work to do, but exciting work.
Absolutely.
Also, Srikanth on Facebook asks, when will it exactly launch? Which we just covered at the end of next year.
That's right. Yeah, the exact date is always a little uncertain because of the different things that happen during integration, but we're shooting for somewhere between October 22 and January 23, somewhere in that range.
All right, well, we'll be looking forward to it. And good luck to you and your team, Paul, on getting it all assembled. And thank you so much for being here today.
Thank you. My pleasure.
Now remember, if you want to ask one of the team members a question, we've got about another 15 to 20 minutes, so still pop those questions into the comment box and we'll make sure that they get them from you. And once again, we are in the Space Assembly Building here at NASA's Jet Propulsion Laboratory. The clean room is right down below me, and you can see all of the pieces that are coming together right now. And we can check out how NISAR is taking shape right down below us. And there's a lot of really amazing technological advances that are happening with this spacecraft. And here to talk to me a little bit about that is the instrument manager, Wendy Edelstein. Thank you so much for being here today, Wendy.
Thank you so much. I'm glad to be here.
So it's only been a couple of days since this new hardware got here. How do you feel? Are you excited seeing it all come together?
I am really excited. I have been working on NISAR for over 5 years, and I've been working and collaborating with India this whole time. I went on my first trip back at the very beginning, so we've been working very hard to bring these 2 systems together. But only right now, last week, that we got the second instrument. So, we've been designing these independently, these 2 separate, very powerful systems. And just right now, on at JPL, we're bringing them together. We're going to be testing them over the next few months. So it's very exciting.
And NISAR has a wavelength longer than most Earth satellites. Can you tell me what that's going to help it do?
Sure. So Paul talked a little bit about its capabilities with the longer wavelength. So you might think of the electromagnetic spectrum. So, at the one end of the spectrum are those short wavelengths, UV and X-rays and the visible light, and those have certain capabilities. But we're on the other end of the spectrum. We're at the RF, or radio frequency end of the spectrum, microwaves. And on that side, it's much longer wavelengths, about 10 centimeters. And from that, we can actually penetrate not just through the clouds that Paul mentioned, but also we can penetrate below the surface. So what we can actually see with this dual frequency system, so while the L-band system operates at about 10 inches, the S-band system that the Indians are providing is about 5 inches. And what that helps is the S-band system looks more at the vegetation and the crops and the things on the surface level, and the L-band system can penetrate below that, look at the tree trunks where the carbon is, can look actually even at, penetrate the land surface, so they can actually look at more geological features. So combining these two systems, we actually have one of the most powerful systems that's ever been built.
So if you were talking to someone looking at the electromagnetic spectrum, where does it all fit? A lot of people think, okay, visible is right in the middle.
Right.
Then you got the short, then you got the long. So where does it all fit
So
in
we're
there?
pretty far. We're a long wavelength. We're on the far end of the spectrum. If you think about it here, the visible's kind of in the middle. X-rays are way over there. Gamma rays way over there. We're on the other end. We're pretty far on the right side of the spectrum. This long wavelength is, that's why I said 10 centimeters can, 24 centimeters or 10 inches lets us see right through the trees and all the leaves and get right down to the surface properties.
Which is really what sets NISAR apart.
That is right.
Right. No other satellite's been able to penetrate all of that 24/7.
Right. And with the two frequencies, we actually can do two things. We can penetrate, but we also can see the biomass or the trees and vegetation. So we can see both of them. And by combining all that data, they are seeing the world in a whole different way.
Yes, in a whole different light. I love it. All right. Now, Jane on Facebook, getting to another social media question, asks, awesome information. What is the projected longevity of this satellite?
So we design it to last 5 years, but generally, when we build space systems, we build them to last. So we anticipate it could last 10 or longer years, but we plan for 5. We hope for 10, 15, 20 years.
Yes, for sure. And Logan on Facebook asks, does NISAR use solar panels for power?
Yes, we do.
We've got some pretty exciting activity going on behind us, Wendy.
Yeah, so you saw that Paul pointed out the instrument that just arrived back in that corner, but right here in front is kind of exciting. This is one of our test structures that we use to actually, right now, the people up there on the scaffolding, they're actually preparing to integrate that big dual frequency system into that system. And so they're getting up there, getting all ready to start integrating the hardware into that. They're making sure they have room for all the cables, and there's not going to be any hardware that will hit anything else. So this is a really important practice run that they're doing right now as you're witnessing it.
And so tell me a little bit about it. Now, a lot of people saw people in the clean room from Perseverance, and they had to wear a much heavier suited.
Oh, right. Yeah. So we have slightly more relaxed requirements. We are on a planetary mission, so we don't have to worry. It's a term called planetary protection. We aren't going to harm our own planet, so we have less requirements. So right now, what we basically have to wear our clothes is just to protect the hardware from particles. We don't want particles to get on anything and put dust somewhere where we don't want it to be. So we have less requirements on that.
And this is pretty interesting because I've seen it actually horizontal, and now it's completely in the vertical. Is there a reason why you do that shift up and down?
Yeah, so this we have this fixture that is used to rotate horizontal and vertical. Some things we need to do in the horizontal configuration. If you can see what we're doing over there with the actual flight system, that's all horizontal because we're going to be testing in that configuration. We're going to be radiating through our antenna, through this wall you might see in the background here. So there's a lot of activities that we do that are better suited for that configuration. But when it's time to install the big antenna that you're not going to see today because it's not here yet, but we have a very large antenna, and that's best to integrate in this vertical configuration. It's also much easier to install our flight, the instruments in a vertical configuration because it's easier to deal with gravity effects in this vertical configuration. You don't have to worry about things not quite fitting right. So this is preferred for integrating our hardware, and then we can go back and go flat if we need to do some more testing. So it's flexible.
That's great. And you were talking about the reflector, which is the size of a 3-story building. So try to wrap your head around that. But we've got a model here that you're going to be able to show us exactly what they're trying to do behind us and then compare it to the model.
Right. So you got a good feel for what this portion of the structure looks like. You can see this is all the radar instrument. This is the feed here. But this up here, this is our big 36-foot antenna reflector. It has a 9-meter boom. It's got this very interesting reflector that's super lightweight. It's only a few hundred pounds and has to be folded up very small and compactly because it has to fit into a pretty small launch vehicle. So it has to compactly stow in this configuration, and then it folds itself around this structure so that on launch it's pretty small. It's not much bigger than this structure right here, but it becomes a very large antenna. The antenna itself is an interesting technology. It's called a mesh reflector, which is like pantyhose that you would wear on your feet. So it's super lightweight. And then we have a nice structure that makes it nice and stable so that it points just where we want it to point.
And tell me a little bit about the integration, Wendy, of the L-band and the S-band, because that's basically the next step for your project.
Right. So I'll walk a little bit back over here. So over the next month, we will stay in this exact configuration. First, they're testing the 2 systems by themselves, just like India did their testing in India, and we're finishing our testing at JPL. But in about 3 or 4 weeks from now, we're actually going to start physically and electrically integrating the 2 systems. That'll take about a month or so to fully test the 2 systems together, make sure that they work together, that they operate synchronously with each other. And then we will then take, then it's when we take that structure, bring it over here and use this big one that we were just looking at before, turn it vertical, and that's when we start working on integrating that big antenna into it. And then after that, we go through a whole bunch of environmental tests with thermal, dynamics, vibration to make sure we can survive the launch, and then we ship it back to India.
And it will be launching from India.
It will be. So in India, there's still a lot of work to go. We have to marry this with that spacecraft. We talked about the solar panel, so there's a lot of hardware at India that's still getting put together. So this instrument will go back to India, integrate it with the spacecraft, and then we will launch it.
Now, when you found out that you were going to be working on NISAR, what were you the most excited about?
Well, I've worked on a lot of radars, with Paul for that matter, so I've done a lot of radars. This is probably the most sophisticated radar I've ever worked on. It's one of these radars, an L-band system, is very complicated and sophisticated, and we're building 2 of them, so that alone is very exciting. And I have to say that the Indian collaboration has been very exciting for me. I had never actually left the U.S. before I started on this project, so my first trip out of the country was to India. So I thought that was really exciting too.
And that's amazing. You had mentioned the collaboration, and that time change must be a little brutal.
It is. In some ways, it's great. We are working 24/7, right? Yes. We always are. We're 12 hours apart. So when it's our morning, it's their nighttime. So we're just working around the clock together.
That sounds great. Well, thank you so much, Wendy, for breaking down all the components here. And as we continue to prepare, just make sure that you stay tuned and you follow us on all our social platforms at NASA JPL, also at NASA Earth. And as I mentioned before, we have a great new article that we can link in the comments box that will actually give you a much more in-depth look at the mission. But I'm going to let you take a sneak peek behind me because this is pretty amazing what's going on right now. We've got a lot of action in the clean room here at the Space Assembly Facility, and it is just amazing to be able to see all of this coming together. The parts just came from India about 2 days ago, as Wendy mentioned, and now they are slowly but surely continuing to work on the satellite here at JPL until it is ready to be sent for that final integration in India, where it will launch from the Satish Dhawan Space Center in Sriharikota, India. And to get the very latest on that mission, as I mentioned, follow us here at NASA JPL as well as at NASA Earth for the very latest information. And from our home to yours at NASA Earth, your home is our mission. Thank you so much for watching.
Wherever, however, whenever. We're here, there.
Hi, everybody. I'm Soledad O'Brien. I welcome you all to Hispanic Heritage, El Ayer y El Mañana, yesterday and tomorrow. You might know me from my work in journalism and television, but one thing you might not know is my connection to this wonderful month-long celebration of the Latino community. My mom, who passed away a few years back, immigrated from Cuba as a teenager, eager to get an education in this country, and also hoping for a country that would guarantee her more freedoms. In 1968, California Congressman George E. Brown pushed to recognize the contributions of the Latino community, and Congress passed Public Law 90-48, officially authorizing and requesting the president to issue annual proclamations declaring September 15th and 16th to mark the beginning of what was then called National Hispanic Heritage Week. Today, we're celebrating that special period of the year when the U.S. recognizes a community that is hardly a minority anymore. We are 60.6 million strong, a record 18.5% of the total population, and growing quickly. Our music, our art, our language, our food have all had a profound influence on American culture. We've even been heard in the voting booth. Our program today will focus on the creation of the Latino Museum, another congressional recognition of the accomplishments of our community. We will also have a conversation about what the future could hold for two leading agencies, the Smithsonian Institution, which is now leading the planning and the development of the museum, and NASA, the global leader in space exploration, science, and research. It is a measure of how far the Latino community has come since that day when Congress initiated the celebration that two such august institutions are at the forefront of our discussion. Joining me is Dr. Ellen Stofan, the Undersecretary for Science and Research at the Smithsonian. She oversees its science research centers, as well as the National Museum of Natural History and the National Zoo. Her focus is the Smithsonian's collective scientific initiatives, especially biodiversity, global health, climate change, species conservation, astrophysics, and the search for life outside the Earth's solar system. Before joining the Smithsonian, Dr. Stofan had 25 years experience in space-related organizations and a deep research background in planetary geology. It's so nice to see you, Dr. Stofan. Thanks for talking with me.
Oh, thank you for having me here today.
Of course, my pleasure. Let's first and foremost talk about the National Museum of the American Latino. That legislation to create that museum was passed just this last December. Can you give us an update on where this stands and what are some of the milestones that have been set for making progress along the path to getting it actually created?
We are so excited about the creation of this new museum, along with the American Women's History Museum. To have the challenge of doing two new museums at the same time is obviously a big challenge, but this is so, as we're going to be talking about today, this is just so incredibly important. And the exciting news is we've actually made a fair amount of progress. We have a search firm on board. We're searching for the director. Eduardo Diaz, who is head of our Smithsonian Latino Center, is the acting director while we search for a permanent director. We've appointed a 19-member board and will continue to appoint members to that advisory board for the museum to help them think about what is this museum? What is it going to do? How is it going to tell this amazing and complex story of the Latino experience in this country? So we are incredibly excited between the board, the search for the director, and of course there's that very small issue, where are we actually going to put this museum? And so we have a site selection process that's going on for both of the new museums. That process is obviously a complicated one. You have to really say, where on the National Mall or near the National Mall do we have the space to put two new museums? And so it's really that site selection that is the first really important step, way before you ever get to the actual design of the museum. And so again, those things are all underway, really exciting.
So you think that Latinos could have a place, a presence on the National Mall one day soon-ish?
Yes, definitely. And, obviously, as our Secretary Lonnie Bunch knows, going from having the congressional legislation to actually getting the museum built on the mall can be a long process. But we're really hoping that this process moves along. And that's why we've taken these steps of actually getting all the leadership in place, because frankly, that is part of the critical step. For those people who don't know, the Smithsonian is actually part federally funded and part privately funded. So about 60% of our funding comes from the federal government, and the federal government usually pays for the construction of museums. But everything that goes inside the museum, all the galleries, bringing in the artifacts, designing the museum, that is actually paid for from private funds that we get through fundraising. And so frankly, that's going to be for both of these new museums, that's going to be a big role of the board, is saying, how do we put together a fundraising campaign to help raise funds for these museums while we go through the federal process? Again, first of all, we have to have this site selection, we'll have to design the museums, and then go through the process of building it. So while it's certainly not going to happen in the next year or two, it is going to happen, and we're really excited about it. And I will say, to give us a preview of how exciting this is going to be, in May of 2022, the Molina Family Gallery will open at the National Museum of American History on the Mall. And that will actually be the first Latino-focused gallery on the National Mall at the Smithsonian. And so that'll at least give us a preview of the kinds of stories, the kinds of things we want to talk about in really saying, how have Latinos helped shape this country? What has been their experience in this country? All these stories that are so critical to tell.
The collaboration between NASA and the Smithsonian is quite deep. Can you talk a little bit about that history?
Yeah, it dates amazingly all the way back to the 1960s. In fact, I think the first agreement was signed back in 1967, where NASA said that all of the significant artifacts from air and space would be, as soon as they were done using them, for technical purposes, they would go to the Smithsonian to be kept in perpetuity. And this is so incredibly important because obviously this is such a story of innovation, of amazing feats done by teams, done by individuals, that the fact that NASA really made this agreement very early on with the Smithsonian means we have all these artifacts to help us tell this story. And of course it started, and the dominant part of the National Air and Space Museum's collection is the Apollo collection. So all of the Apollo artifacts, down to really old containers of pineapple that the astronauts took to the moon, everything went to the Air and Space Museum. So when you see artifacts around the world from Apollo, they're on loan from the Smithsonian, because obviously we wanted to get that story out, not just across the country, but around the world. We also hold one of my favorite things at the Air and Space Museum, which is the Apollo art collection. During Apollo, NASA commissioned all the leading artists of the day to be documenting Apollo from an artistic point of view. And I really love that because I love this intersection between science, technology, engineering, math, and the arts. And those two are really critically important. So we have a Rauschenberg, we have like 5 Norman Rockwells, we have an Alma Thomas that's my absolute favorite. So the fact that the Smithsonian can help tell that Apollo story is because we have these artifacts. And now this relationship continues to today. But NASA now gives the Smithsonian sort of first right of refusal of the artifacts, and then does give them to other museums around the country. It's not as exclusive as it used to be, but that's okay because seriously, we actually run out of room to store things at the Smithsonian.
I've had the opportunity to interview many NASA scientists over the years on my journalistic programs, and it's always been fascinating. But what becomes very clear very quickly is that NASA has this massive portfolio, right? From the home planet to biodiversity to human impact to international space and moonlight, right? I mean, the list kind of goes on and on and on. How do you think you're going to be able to capture all of that and then represent some of that in the National Museum of the American Latino? What's that intersection look like?
Well, when you think about a museum, really what you're doing is telling stories. Again, stories of individuals who made a difference, stories of teams that made a difference. And obviously that story of NASA You know, if you're going to do a story about Perseverance rover, of course you want to, that's on Mars right now, you want to talk about Diana Trujillo, who is a Latino woman who's doing amazing things as part of the engineering team on Perseverance. And so to me, it always comes back to the story. What's the story? Because you might have an artifact, but you really want to know, who is the person that built that? Who's the person that operated it? You know, what struggles did they go through personally to achieve these amazing things? And the story of this country is the story of American Latinos. They've, as everyone knows, contributed huge amounts, been there every step of the way. You know, it took 400,000 people to accomplish Apollo. And so the job of the new museum is going to be to collect all those inspiring stories, some of them not wonderful stories, a lot of them stories of hardship, stories of struggle, stories of prejudice, and other stories are stories of perseverance and triumph and huge contributions to the history of this country. And so for the new director and the curators of that museum, frankly, it's going to be an embarrassment of riches, because there are so many stories out there, and which story do you choose, and which artifacts do you choose? And what is the narrative of the museum going to be? And that's going to be what we're going to be working on as we go through the longer process of actually getting the museum built, is what are the stories? And, you know, so many of those stories at NASA, you know, whether it's Ellen Ochoa, who flew obviously on the space shuttle and then went on to become head of Johnson Space Center, or whether it's somebody we're going to be talking to later here today, Marla from the NASA Glenn Research Center. You know, the Latino story is the NASA story, and that, you know, we want that museum to definitely tell that.
An embarrassment of riches is always a very good problem for someone who's curating a museum to have. Dr. Stoffen, I'm going to have you stand by for a moment. We're going to continue our conversation in just a few moments. I wanted to hear about the great work that is going on, in fact, at NASA's Glenn Research Center and Langley Research Center, leaders, of course, in aeronautics and aviation. So let's welcome the Glenn Research Center Director, Dr. Marla Perez Davis.
Over our 80 years of operations, NASA Glenn has made many contributions to space and aeronautics, from ground testing, materials development, and research perspective. In that time, we have helped NASA explore the solar system. We have made aircraft cleaner, quieter, and safer, and our technologies have changed lives here on Earth. Initially established in 1941 as an aircraft engine research laboratory, NASA Glenn now contributes to a variety of NASA and commercial aerospace missions through our expertise in aircraft and space technology. Glenn is helping the United States send the first woman and the first person of color to the moon. Our world-class test facilities and unrivaled expertise in power, propulsion, and advanced materials are crucial to advancing Artemis. Glenn is conducting revolutionary aeronautics research in green technologies like electric aircraft propulsion and advanced materials and alternative fuels for sustainable aviation, while also exploring next-generation supersonic and hypersonic aircraft. Our Neil A. Armstrong Test Facility in Sandusky is home to the world's largest and most powerful space environment simulation chambers, and it has been instrumental in preparing the Orion spacecraft for the Artemis 1 mission later this year. NASA Glenn is advancing human spaceflight through our leading roles in power and propulsion communication technologies, advanced materials, and through our world-class test facilities. Our center played a critical role in the development and testing of the Orion spacecraft for Artemis 1. And we will look on with pride at its flight around the moon and back to prove the systems and technologies needed to safely launch astronauts on Artemis 2 in the coming years. We are finalizing the design of the power and propulsion element for our lunar gateway. Once integrated and launched with the habitation and logistic output, it will form the cornerstone of our exploration architecture around the moon. And its innovative high-power propulsion system will provide more access to lunar surface while demonstrating those technologies for future human exploration of Mars. NASA Glenn will continue to meet future surface exploration needs by advancing a broad portfolio of cutting-edge power generation and distribution systems, including radioisotope, fission, and solar, that will work together to ensure future missions have the plentiful, reliable power required to be successful. NASA's vision of flight looks very different from today's world, and we believe we are at the right place at the right time, and we foresee a future commercial aviation renaissance unlike any other. We see electrified propulsion as one of the key drivers of changing the way we travel, making future aircraft cleaner, more efficient, and more cost-effective. We are tackling the challenges of electric propulsion for small to large aircraft. Our focus is on the development of all electric propulsion systems and components, from batteries to megawatt scale systems. And we are partnering with industry on future large-scale hybrid electric concept to meet NASA's requirements on carbon, fuel burn, emissions, and noise. We are rallying emerging markets to tackle the challenges of creating an air transportation system for urban and underserved areas that is all electric, autonomous, efficient, and safe for moving passengers and packages. At Glenn, we are studying how electric systems can be optimized, and we are supporting engine and power technology development. We're also working to understand and mitigate the vehicle's acoustics to help limit noise issues. And we are developing secure data links and real-time communications to safely integrate these aircraft in the national airspace. We are building an experimental airplane called the X-59. It flies at supersonic speeds, but makes a quiet thump instead of a loud sonic boom. We will fly it to provide data to enable regulation changes to allow overland commercial supersonic flight. This project is a game changer for future transcontinental and intercontinental transportation concepts, and will provide an opportunity to generate economic and societal benefit in a globally linked world.
To talk a little bit more about the exciting work the Hispanic workforce is supporting at Langley Research Center is Engineering Project Manager Debbie Martinez.
Thanks, Soledad. The Convergent Aeronautics Solution, or CAS project, is helping NASA change the way airplanes fly and the aviation industry along with it. By providing innovative solutions to complex problems, CAS seeks to help all of NASA aeronautic research and the broader community to the benefit of the U.S. economy and our quality of life. As the CAS Execution Manager, I have worked with numerous talented and creative researchers, such as those on the STEREO team. STEREO stands for Scalable Traffic Management for Emergency Response Operations. We are here at Langley Certain Range. The STEREO team had flight tests here. They partnered with the California Department of Forestry and Fire Protection and the U.S. Forest Service, who flew aircrafts that help fight wildfires in coordination with our NASA drones, using the STEREO system to keep all parties informed. The increased communication and coordination from the ground units to the vehicles in the air helped make the battle against wildfires faster, safer, and more targeted. Let's take a look at other aeronautic programs that some of my Hispanic colleagues are supporting.
I work for the Advanced Air Transport Technology Project, and we're focused on exploring and developing technologies to improve energy efficiency and environmental compatibility for fixed-wing subsonic transport. What is that? Those are passengers and cargo aircrafts. These studies look at vehicle configurations that are 3 generations beyond what we currently are using. For that, we need to have mature technology solutions ready for the time frame of 2035 to 2045. Recently, at 14x22, we tested the Common Research Model on the simplified high-lift configuration with active flow control. And active flow control is one of the technologies that we're trying to develop, where it manipulates the flow around a wing to make it more efficient. All these studies are super exciting because it will impact positively the way we travel in the future.
The facility you have behind me is the Copy in Motion facility, which is our premier world-class facility that consists of 3 high-fidelity, full-mission, human-in-the-loop flight simulators and 1 6 degree of freedom motion platform. My job here consists of leading a team of engineers and technicians on the planning and execution of operations, maintenance, and improvements of the flight simulators and the motion platform. Flight simulation is a safe and cost-effective way to train pilots and design aircrafts. It also allows us to develop new technologies to improve the decision-making of the pilot and also response to emergency situation in the cab. Flight simulation is definitely an important factor in keeping the commercial aviation safe for the flying public.
The Electrified Powertrain Flight Demonstration Project is part of NASA Aeronautics' focus to expand research on sustainable aviation through the development and test of green technologies for the next generation of aircraft. NASA and industry have conducted studies on electrified aircraft propulsion concepts, and the results indicate that there is significant reduction in energy use, emissions, which reduces our carbon footprint, as well as a reduction in direct operating costs, which will benefit both the public and airline operators. Through industry cost-sharing partnerships, the Electrified Powertrain Flight Demonstration Project is working to mature and flight test megawatt-class electrified powertrain systems, which are at the heart of electrified aircraft propulsion systems. This is a game changer. If we can actually introduce megawatt-class powertrain systems, we can change how aviation aircraft are designed in the future, with applications to turboprops, regional, as well as single-aisle aircraft.
New airspace operations are rapidly emerging involving multi-rotor vehicles. Small quadcopters and octocopters are being proposed for applications such as surveillance, photography, or even package delivery. The System-Wide Safety Project is developing tools that are critical to the safe integration of these vehicles into the national airspace system, which is particularly important for urban environments with a high population density. So the work that I'm involved with is developing flight dynamic simulations that can accurately predict the vehicle's trajectory, the vehicle's performance, and simulate different air traffic management scenarios. And so we complete different wind tunnel tests to assess the vehicle's aerodynamic behavior in a wide range of operating conditions. This ranges from hover all the way to forward flight. It's definitely an exciting time to be a part of NASA and shape the future of aviation.
Thanks for joining us at NASA Langley Research Center in Hampton, Virginia. Back to you, Soledad.
NASA is doing an incredible amount of work in Earth science, specifically with efforts to understand our Earth's atmosphere, crust, water, and life as a single connected system, and understanding the Earth system and its response to natural and human impact give us a better understanding of our continuously changing climate. These studies and insights are necessary to determine how to predict future changes of climate, weather, and natural hazards. So here to give us additional insight into these efforts is Earth Science Deputy Director, Ms. Sandra Kaufman.
Thank you so much, Soledad, for that introduction. NASA Earth Science conducts a very comprehensive program of breakthrough science research on climate science. We use our 23 space missions that we have in collecting all kinds of data. We have another 16 missions that we have under development that are going to be launched in the next several years. We also use the International Space Station. So with all of these missions and instruments aboard the space station, we measure aerosols in our atmosphere. We try to understand whether they come from natural sources or man-made sources. We also study the processes that regulate the abundance of ozone in the atmosphere. There is such thing as the ozone hole, and we measure it, and we can predict certain aspects of it. We study sea level rise. We only have one Earth, and we are helping to the best that we can in understanding it and measure what's happening. Earth Science has a very strong applied sciences program, and in that program, we not only do disaster response due to natural hazards, we also have a program on public health, helping predict illnesses such as malaria, chikungunya, in a lot of the countries in South America, Latin America, and Africa. That is a big problem. And we are trying to use our satellites, the measurements of temperature, the measurements of moisture, and try to predict the incidence of some of these illnesses. We also have a very strong agricultural program that is helping farmers out there in not just on scientific studies, but trying to understand, for example, soil loss, soil moisture, plant evapotranspiration, whether the soil is not in good condition, whether the soil is releasing carbon into the atmosphere as carbon dioxide. And so all of these aspects are the aspects that we work and help and study. And of course, working with local communities, working with people in coastal areas with the sea level rise, and helping anticipate aspects of resilience, community resilience, and such. So last, I wanted to talk about our Surveyor program, an initiative that we have with the United States Agency for the International Development, USAID. And we work in partnership with leading regional organizations worldwide to help developing countries use this information provided by our satellites. And empowering local communities all the way from West Africa, South Africa, the Himalaya region, Central America. And we are planning on opening up a new hub in Central America in the upcoming years. So all in all, Earth science is trying to contribute to the understanding of our planet, but also help with all kinds of aspects that benefits society in general. So thank you very much, and back to you, Soledad.
We just learned about the work being done here on Earth, so now let's take a look above. Another interesting and exciting research area that NASA works on is space food. Food is critical, of course, for mission success and the health and performance of the astronauts. Maintaining a healthy diet plays an important role, specifically socially and psychologically, which is important for long-duration missions in space. So how does NASA handle feeding its diverse crew members? Let's turn it over to Johnson Space Center.
Thanks, Soledad. My name is Gisela Munoz, and I'm a crew systems instructor in the Flight Operations Directorate. One of the lessons astronauts receive from our team is food preparation and equipment, which covers not only how to operate the galley hardware, but also what types of food they can expect to see when they're on orbit and how to prepare them. Space food is prepared and packaged differently than on Earth. A standard menu for astronauts will include rehydratable foods and beverages, thermostabilized foods that are packaged similar to military MREs, and natural form foods like nuts or cookies. If you're lucky, you'll get food from one of our international partners like Russian, European, Canadian, or Japanese space agencies. Astronauts also have access to fresh food like apples and oranges that are flown up on our commercial resupply vehicles. Eating and drinking in space is different than on Earth because of the lack of gravity. Since you're not able to pour drinks into a cup, beverages are packaged in a pouch and sucked out through a straw. For your food, you need to be careful as you eat because even small pieces of food don't normally fall off the table like they do on Earth, but they'll float away, and hopefully not at one of your fellow crewmates. One popular Hispanic food used in space are tortillas. Tortillas are a staple food and native to Hispanic cuisine in Mexico, Central, and South America. Tortillas have been used on orbit for decades for crew meals as early as the beginning of the Space Shuttle program. Astronauts have gotten creative over the years with using tortillas to make pizzas, fajitas, breakfast burritos, and even a space cheeseburger. Tortillas are a great component to the standard menu because they don't create a lot of crumbs and have a longer shelf life than the standard breads we eat on the ground. Shelf life is important because astronaut meals are sent up to the International Space Station in advance. In addition to the standard menu, astronauts are provided a small sample of off-the-shelf foods they request to fly. Some recent requests have included Hispanic foods such as salsa casera, bean dip with jalapenos, and tostada shells. Salsa sacera is a red sauce dip made from chili peppers, red peppers, onion, garlic, and tomatoes. Tostada shells are similar to tortillas, but have a crunchy consistency. Avocados even made a recent trip up the ISS aboard one of the resupply vehicles. It is important to incorporate this variety into everyday meals and take crew preferences into consideration. The acceptability of astronaut meals are a contributor to the positive psychological health and performance of the crew while they are in space. Gathering for meals with friends and family with good food is an important part of the Hispanic culture. Entire songs have been dedicated to the menu of Hispanic cuisine, such as El Menú. The opportunity to have the comforts of home cannot be understated. This will be equally important as we venture farther from home during the Artemis missions.
And it's back to our conversation with Dr. Stofan. So given this long-standing partnership between NASA and the Smithsonian, how do you see them working together on the Latino Museum? What would that actually sort of look like in practice?
Well, you know, one of the things that NASA is constantly think about is how do we help inspire that next generation? And that's actually also the mission at the Air and Space Museum. And I know it's the mission for the whole Smithsonian is really thinking about how do we inspire the next generation to do more, to discover more, to invent more, you know, to keep this great story of this country going. And so when I think of the Latino Museum and NASA working together, one of the things I really think about is first of all, going back to Marion Wright Edelman's quote, you can't be what you can't see. And so are we highlighting people like the astronaut Franklin Chang Diaz or Joe Acaba, who you're going to talk to, or Ellen Ochoa? Are we really telling those stories of people like Diana, of people like Marla, these amazing engineers, so that every kid who walks into that museum understands that people who look like them have been making incredible contributions all along. And I know that's really important to NASA, and I know it's really important to the Smithsonian, that piece about inspiration. And then, of course, it's always the programs. It's not just the artifacts, which are critically important, that help us tell the stories. It's not just who we're featuring, but what kind of programming, what kind of educational reach, so that certainly people who come to the museum are being inspired, but we're also creating digital outreach, using all those incredible skills that NASA has and the Smithsonian has together to really make sure we're not just reaching kids who can come to Washington, but that we're reaching kids all around this country and all around the world.
Currently, NASA is preparing for return to the moon, and there are a handful of Hispanic astronauts who are working to make that a reality. This means that they could be the very first Hispanic astronauts to ever set foot on the moon, which is amazing.
No, it really is amazing. And you know, I'm old enough that I remember the first moon landing. And while it was certainly inspiring, and actually my dad worked at NASA at that time, it didn't make me think I'm going to go do that, because frankly, none of them looked like me. And this idea that those first crews that we send to the moon, the multiple crews we'll send there, and then the first humans that walk on Mars, they're going to look like all of us. And to me, again, it gets back to that inspiration. If we can do this, if we can do this together, just think what kind of power we have. And to me, that is part of the inspiration of space exploration that I think has helped certainly bring this country together during Apollo. But I think, you know, now as we really struggle with COVID, I think we need a little of that moonshot feeling of, you know what, if we put our minds to it, we can do anything. We can have humans walk on the moon.
I love the concept of storytelling as a way of both bringing people together, but also really making people recognize themselves. I mean, this idea of like including everybody's story in that bigger storytelling picture. Dr. Stofan, we're going to take a break in order to hear from the astronauts, Dr. Frank Rubio and Joe Acaba, who are going to tell us a little bit about what this means for them.
All right, Frank. So, you know, here we are in Hispanic Heritage Month, and I think it's really important because it gives us that time to really reflect upon the contributions that the Hispanic community has contributed, not only to the space program, but to the U.S. As a whole. So it really just gives us an opportunity to reflect on all the work that we've done, the contributions that we have given, and really to celebrate that, and for us to remember our heritage and to take part and really focus our time on that.
Yeah, Joe, I agree. I think it's a really important thing that we celebrate, right? We as Americans, I think one of the great things for our nation is that we are made up of so many backgrounds and cultures. And I think acknowledging where we came from, for my kids, I want them to be really proud to be Latinos or Hispanic Americans. And despite the fact that, they're American to the core, I don't want them to forget where they came from, where we came from. And so as a nation, I think throughout the year, the fact that we're able to celebrate different cultural backgrounds and diversity is just great, because I think more than anything, it acknowledges that as a country, we're made up of a whole lot of different backgrounds that came together and made this awesome thing named America. And I think together, those cultures and those backgrounds can accomplish and continue to accomplish amazing things.
So I think when we talk about, having whatever culture it may be, working at NASA, it's super important. I think everybody understands today that a diverse team makes for a better team. You get different perspectives, different ways of doing things. So that's super important. And being an astronaut, it is a visible occupation. Frank and I, we're just a couple of ordinary dudes from California, but we have a really cool job, and it's an important job, and it's very visible. And so, part of what we do is representing NASA, but then also representing who we are as people. And so I think from the NASA side, that's super important. But when we go out and, either when we give talks or when we go and do our missions, people are watching. When I was first selected as an astronaut, the Puerto Rican community, they just embraced me. They were proud. They reached out to me. And then as I flew on my shuttle flight and then future flights, that support just continued. And as I give talks and I talk to kids, they look at that and they go, dang, if Joe can do that, I can do that. And that's not belittling to me. It's just I'm a regular person that, had a dream, and it happened to work out. So I think it's important for NASA, and I think it's important for the Latino community to see me and Frank and others that are doing this work, representing them and, trying to make them proud.
Yeah, Joe, that's an awesome way to put it. Like you said, we're just blessed to have this awesome job and to represent the NASA team. Right? We represent thousands of people that just put in so much work and effort to make what we do happen. And I think people forget. Yeah, you look at my class, for instance, and we're an incredibly diverse class. But first and foremost, within our core, competence and capability are utmost, because ultimately we're trusting each other with our lives. And so when I look at Joe, it's awesome that he's Hispanic, right? And that I know that he's reaching a large portion of our society. But really, when I see Joe, I see an incredibly capable, competent astronaut, and that's who I want beside me. Not just because he's Latino, but also because, and really mostly because of who he is as an astronaut, as far as being capable, knowledgeable, and competent in what he does. And I think all of us take a lot of pride in that. When I think about the moon and going back to the moon, I honestly go back to being a kid mode, right? I personally don't care who it is. It's going to be hopefully one of my peers that's in the Corps now. And just thinking of my friends being up there, it just makes me excited. And not just because I'm an astronaut, but as a person, as an American, as a human being. I just think accomplishing great things brings us together because we're all excited about being able to point and say, wow, look what we're capable of doing when we put our efforts together and work hard and overcome obstacles and take challenges head on. So Excitement, happiness, joy. I mean, it's hard not to smile when I think of going back there. I look forward to hopefully contributing as an NASA team to accomplishing something that, I think we can imagine it right now, but we can't even dream of how awesome having a community on the moon in a permanent or semi-permanent state is going to be like. It's going to be pretty cool. It's going to be hard, but I think it's going to make it even better. The fact that it is hard is going to make it even better for us to be able to accomplish those things.
Yeah, when I think about all of us going back to the moon, and if I just had to say a few words, it would be, you know what? If we can do it, you can do it. And that sounds very simple, but it takes a lot of work. It's going to take a lot of work for us to go back to the moon, and I think it signifies that amount of work, that amount of dedication. So, whatever the younger generation wants to do, just know that if we can do this, if we can get back to the moon, you can accomplish what you want to do. We're not working every day thinking about a legacy, but it is important for us to realize that people do look up to us as a role model. And I feel proud that, we both are leaving a mark, to our country, to where we came from, and just the world in general. So I think, the most important thing is being a good person, and working really hard. You're not always going to be the best at any particular job, but you can work hard. You can make yourself proud. You can make your family proud. And I think that, when I start thinking about a legacy, I'm hoping that's what people will remember is, Joe was just this regular old dude, but, he worked hard. He was a good person, and, and I can be proud about that.
Right. We, as a Latino community, tend to bring a lot of joy and celebration to the picture. And I think nowadays, especially, our nation needs a little bit of joy. And so as we reflect and as we celebrate, trying to stay focused on, yes, we're in a hard period in our history right now, but we're going to overcome this. And we're going to look back and say, hey, we did it. We got past that. And now it's time to keep moving forward. And so let's celebrate, enjoy, take pride in who we are, and then keep moving forward. Adelante.
Back with Dr. Stofan. Washington, D.C. has a lot of museums, Why this one? What will make it different? Why would you say people have absolutely, positively have to go to this museum when it's finally built and completed?
When I think of all the Smithsonian's, and for example, you could argue we already have a Museum of American History. Why do we need a museum just about the Latino population? But when I look at our Museum of Native American Museum, when I look at the African American History and Culture Museum, those museums show the richness and the depth of the stories and the contributions that have made this country what it is. And I think to be able to highlight stories that frankly people just don't know. I mean, how many people know who Felix Carrera was? I mean, he was a Puerto Rican World War I fighter pilot hero. Every kid should know his name, and this museum will give us the opportunity to tell more stories, to talk about the contributions that Latinos have made to this country, but also to show the darker side. What have been the struggles? What have been the challenges? And I think that for those of us who really think about the rich, rich heritage that goes back hundreds of years in this country, those stories need to be told. They need to be more commonly understood. And it is the American story, and it's the Smithsonian's job to tell the American story. And the Latino Museum will give us more space, more room, more bandwidth to make sure that everybody's story gets told.
Many museums focus a lot on history, sort of ancient artifacts. It sounds like you're going to have to figure out how to toggle between the history, the historic story, but also the unfolding present as well.
Our Secretary Lonnie Bunch of the Smithsonian likes to talk about the fact that the role of the Smithsonian, and really the role of museums, is to help people understand the present in the context of the past, and to help us chart a better future. And so when you think about that, we should be using history in all these museums to help us understand how we got to the place we are today, because hopefully that'll help us understand what's happening. It gives you a very different interpretation of what's happening right now if you really understand the path we walked to get here. And then when you think of that path, it helps you understand, how do we get to the future that we all have a role in creating? And I think sometimes a lot of us feel like the future is something that happens to us. It's not something that we have agency in. And to me, at the Smithsonian, we're telling the stories of the past. We're involving people in the excitement of what's happening now. But it's all with the idea of how can the public then use that information to help create the future that we all want.
NASA is obviously continuing its work on inspirational missions that capture the imagination of many. I know that currently the agency is exploring foreign worlds, looking to get humans back to the moon, as I mentioned, all while expanding our understanding of the planet. Through its work, the agency hopes to continue to inspire young people. You've mentioned that several times. I know that's a real piece of the mission, or the missions, is to make sure that young people are constantly inspired and of course spark an interest in science and research and exploration. So I thought it would be a good time to hear from the workforce at the Kennedy Space Center in Florida and Jet Propulsion Lab in California on some of the work that inspiring Hispanics are doing.
Happy Hispanic Heritage Month from NASA's Kennedy Space Center in Florida. I'm Liliana Villarreal, Operations Flow Manager with the Exploration Ground Systems Program. I'm supporting our return to the moon through NASA's Artemis missions. I'm responsible for the overall management, planning, integration, and execution of operational ground and flight hardware activities required to support Orion and Space Launch System human spaceflight missions. My responsibility is to help lead the team to ensure we successfully complete the ground processing tests and assembly in preparation for the Artemis 1 launch. I was born in Cartagena, Colombia, but consider Miami, Florida my hometown. I moved to Florida with my family when I was 10 years old. The fact that this is the foundation for going back to the moon and eventually going deeper into space is such an inspiration for me. To be part of the team that started that is a dream for an aerospace engineer like me. We are very fortunate in NASA to have a healthy and strong Hispanic workforce. Most of them are very much involved in mentoring and sharing their knowledge with the younger workforce, but a lot of us also do outreach with the public and most importantly to the K-12 grade students. I think it's important to ensure people see that we do have Hispanics and other minorities working these amazing, complex, and exciting programs, because we need to show everyone that a diverse team is a successful team. I am Artemis. We are Artemis. As we prepare to launch missions to the moon from Florida, get to know one of the team members behind the Mars 2020 mission from the NASA's Jet Propulsion Laboratory in California.
Happy Hispanic Heritage Month from NASA's Jet Propulsion Laboratory here in sunny California. My name is Elio Morillo, and I'm a test and operations engineer from Mars 2020. I've worked on the Perseverance rover, as well as the Ingenuity helicopter. Currently, I'm the engineering operations mechanisms lead. So my team and I make sure that the rover is healthy on the surface of Mars every single day, that it's roving, as well as collecting samples. These samples are going to be one day returned by our follow-on mission, the Mars Sample Return Mission, which is going to be in charge of taking these samples from Mars and bringing them back to Earth, something we've never done in history and we're very excited about. One of the reasons I came to JPL is because we live at the cutting edge of space exploration. And along with that, we have a very diverse workforce. I was born in Ecuador, grew up in Puerto Rico, lived in New York City for several years, went to school in Michigan, and came here to California. Here at JPL, I've found an incredible supportive community of engineers and scientists, particularly through the employee resource group Amigos Unidos, where I've found my family away from home, my familia. Through Amigos Unidos, we've created a supportive network that serves as a community both on campus and outside. I've been able to find mentors that have taught me leadership as well as technical proficiency. And through several outreach events, such as the open house, high school initiatives, the summer internship program, we continue to inspire the future generation of engineers and scientists to continue this legacy of space exploration. The great thing about NASA is that alongside the engineers and scientists, we have social media specialists, graphic designers, storytellers, business administrators, all different kinds of skills and levels of expertise that help us push all the many missions of NASA forward. It really does take a village. And now, let's hear from our friends and California neighbors at NASA Ames Research Center.
Hi, my name is Cesar Acosta. I've been working here at NASA Ames Research Center for the past 27 years. 20 of those being right here at the ArcJet facility. Here at the ArcJets, what we do is we do heat shield testing. We test material for entry into an atmosphere, making sure that that material that goes on board a spacecraft is safe. The Hispanic team members that we have here at the ArcJet facility consist of test engineers, technicians, electricians, and data acquisition. I've seen that grow in the past 20 years. It makes me proud to see a bigger Hispanic community here. And as a Hispanic, it gives me great pride to be working here at the ArcJets and just being part of this team.
Dr. Stofan, it all sounds very, very exciting. How do you advise people to keep up with all that's unfolding as we're on this path to creating the museum?
Well, a couple different ways. First of all is, of course, come to our website, si.edu, which will let you know what's happening with the museum. So when we appoint new board members, that some of whom are pretty famous people that you've heard of, like Eva Longoria or Jose Andres. So I urge people to keep up with who's being appointed to the board. I would also say that you'll be able to see the progress on when we appoint the director later this year. As we go through that site selection process. And of course, as we think about how do we get everybody in the country involved in terms of thinking about the stories this museum is going to tell and the role that it's going to play. So I urge everyone to keep an eye on this, come to our website. And of course, again, one more time in May of 2022, please come to the Museum of American History on the Mall and come visit the Molina Family Gallery. Soledad, of course, you're on the board also of the new Latino Museum. How do you feel about being part of this great adventure?
Sort of like, it seems kind of overwhelming, and talking to you about it makes it seem even more overwhelming. I'm incredibly honored, obviously, and very excited, but already you think, like, well, what is the story of the American Latino? Is it my mom's story, came to this country as an Afro-Latina from Cuba? Is it the story of Americans who are Mexican descent, whose families have been here for generations and generations and generations? There are so many interesting stories to tell that as a journalist, we never even scrape the surface of. So I'm just absolutely thrilled. I'm very, very honored. Thank you for asking me that.
Thank you.
A big thank you to Dr. Ellen Stofan for a great conversation. And I have to say, one of the things that I'm really looking forward to in this new museum is to see so many Americans exposed to the story of our community. We've had an incredible impact on this country, and our ancestors, whether they were our parents or our great-great-grandparents, have been refreshing our country's culture for 500 plus years. Our stories are America's stories. This museum and conversations like the one we just had underscore just how much we have infused American culture with the very best of us. And I think it's also an opportunity to correct some of the mistakes made long before my mom arrived in this country from Cuba. And for many years, a lack of recognition, a lack of inclusion. Our community has been a great part of the American story and society and culture, the arts, schools, government, corporate America. Only 2%, or 10 Fortune 500 CEOs are of Hispanic descent. Only 3% of full-time college professors are Hispanic. Latinos account for just 6% of judges on courts of appeals, 7% of judges on district courts. Though everybody's very proud to have Supreme Court Justice Sonia Sotomayor. There are just 26 Hispanic members of Congress, but passing this legislation to create the National Museum of the American Latino is just the beginning. Now the real work begins. I'm happy to see some of you in this room leading the change. So thank you, thank you, thank you. And a very special thank you to the Hispanic Outreach and Leadership Alliance, HOLA, at NASA headquarters for this opportunity, and to everyone across NASA who participated in today's program. Thank you all for watching. And now let's hear a few words from HOLA's leadership.
Gracias, Soledad. What a joy and honor to have you as our host for today's program.
On behalf of the Hispanic Outreach and Leadership Alliance here at NASA headquarters from beautiful Washington, D.C., we would like to thank you and Dr. Ellen Stoffen for leading such a great conversation about the creation of the Museum of the American Latino. Latino Americans have touched many aspects of our daily lives, and we're excited to hear the stories that will be told through it.
Here at OLA, we work hard to foster awareness and promote the contributions that our community has done here at NASA. So we're looking forward to increase that representation, involvement in our science, technology, engineering, and space exploration.
We would like to thank the NASA employee resource groups across the agency who participated in this year's program. Ames Research Center, Glenn Research Center, Jet Propulsion Laboratory, Johnson Space Center, Kennedy Space Center, and Langley Research Center. Thank you also to NASA leadership for supporting employee resource groups like OLA and for embracing diversity, equity, and inclusion. And now, let's hear from our NASA Administrator, Senator Bill Nelson.
This program marked an opportunity to celebrate and reflect on the contributions and impact of Hispanics throughout our community, our country, beyond. Thank you to Soledad O'Brien, Ellen Stoffen, and all our NASA guests for contributing to this meaningful conversation. And as we heard in the program, Congress passed legislation to build a national museum of the American Latino in December 2020. What a historic moment. I look forward to seeing the development of this future museum and ensuring the full NASA story and the Latino story, that it's captured and shared with the world. As NASA continues studying our home planet, exploring our solar system, and way beyond, and preparing to go back to the moon and then on to Mars, it will take all of us working together to be successful. NASA is committed to a culture of diversity, equality, and unity. Thank you again for joining us in celebrating Hispanic Heritage Month. And a special thank you to the Hispanic Outreach and Leadership Alliance at NASA headquarters, and to the Hispanic employee resource groups all across NASA centers. Onward and upward.
planet Earth against potential future impacts. The test to protect the future of our planet takes place today.
Welcome, and thank you for joining us from Johns Hopkins Applied Physics Laboratory, home to the DART Mission Operations Center. I'm your host, Tahira Allen with NASA Communications, and tonight we're following the real-time journey of the DART spacecraft and its planned collision with asteroid Dimorphos. The Double Asteroid Redirection Test, also known as DART, is the world's
Vale, sí, te veo.
1, 0. Ignition. Liftoff.
Yo también pensaba asteroide fin, pero como me dijeron los de ciencias planetarias que lo iban a hacer ellos de la Universidad de Alicante, que están en el equipo de DART, pues al final no me animé y luego pues pasa lo que pasa. Vale, estupendo.
First planetary defense test mission of its kind. At 7:14 p.m. Eastern, it will demonstrate asteroid deflection technique known as kinetic impact. Rest assured, this is only a test. The asteroid DART intends to impact is not a threat to Earth now, nor will it be after.
¿A ti puedes hablar por sí?
Sí, probando.
Vale,
1, 2, 3.
creo que ya se te escucha. ¿Nos podéis confirmar que se nos escucha?
Sí, se escucha perfectamente.
Vale, perfecto. Bueno, pues mientras hablamos voy preparando cosas que hemos tenido tiempo, pero esto ha sido una improvisación de último momento.
Vale, sin problema. Yo estoy viendo porque como no sé, estoy viendo a ver cómo editar esto para ver qué micrófono pongo.
Vale.
Este micrófono mejor. Vale, estupendo.
Sí, se oye.
Se oye mejor ahora, ¿verdad?
Se oye mejor.
Vale, es que tenía que cambiar el micrófono.
Vale, pues yo ya estoy. Hola a todos, bienvenidos a la cobertura en directo de la llegada de DART, de la misión de la NASA, hasta el asteroide Dimorphos, una misión que se lanzó en el año pasado, a final de año ya, y que por fin vamos a tener el esperado resultado, que será el impacto, el primer impacto que vamos a hacer con el objetivo de desviar un asteroide un poquito. Tranquilos, daremos muchos más detalles. Y nos acompaña como invitado de ultimísima hora, mejor dicho, de hace 10 minutos, Nahum, geólogo en apuros, que ahora le voy a poner su link de Twitter. Bienvenido.
Hola, buenas, ¿qué tal? ¿Cómo estáis?
Pues una misión interesante esta, ¿no?
Bueno, yo creo que es una misión muy interesante por muchas razones, no únicamente la de la defensa espacial, ¿no? Hemos visto, sí que es verdad que en los últimos años, pues visitas a distintos asteroides, hemos visitado pues algunos de camino a Júpiter, los primeros con la misión, por ejemplo, Galileo, luego hemos estado en Vesta, por ejemplo, ya con un mayor tiempo, luego hemos tenido pues un tiempo de estancia en Ryugu, en Venus. Pero esta misión tiene algo de especial, ¿no? Ya que vamos a poner algo más de energía en el asador y vamos a ver qué podemos aprender, no solamente del desvío de asteroides, sino de cómo se comportan, ¿no? ante un impacto. Y sobre todo que, por ejemplo, a diferencia de Ryugu y Venus, que si no recuerdo mal eran asteroides de tipo C, ahora vamos a encontrarnos con un asteroide de tipo S, que es para que nos entiendan los oyentes, un asteroide rocoso, con silicatos principalmente. Y sobre todo del que también hay mucha incertidumbre, ¿no? Vamos a encontrarnos con un cuerpo monolítico, va a ser Dimorphos un bloque o va a ser también una pila de escombros, ¿no? Y creo que, bueno, todas esas incertidumbres añaden también, yo creo que un poco de emoción a lo que se va a poder aprender de esta misión, ¿no? Y por supuesto, obviamente, la defensa espacial, ¿no? ¿Seríamos capaces de desviar un asteroide con un impactador cinético? ¿Cuánto? ¿Cómo? Y dependiendo de qué tipo de asteroide, ¿no? Porque obviamente no, seguramente entre un asteroide monolítico de un solo bloque y un asteroide de pila de escombros, o rubble pile, como se dice en inglés, pues probablemente vaya a haber muchas diferencias, ¿no? Y con este impacto se van a poder modelar mucho mejor y reducir todas esas incertidumbres.
Comentar que yo ahora voy a estar respondiendo dudas sobre la misión, sobre la propia sonda, pero si tenéis alguna duda sobre el asteroide, cómo es, cómo se ha formado o cualquier curiosidad, os animo a que hagáis la pregunta ahora porque no creo que vaya a estar todo el directo. Y realmente geólogo en apuros es un geólogo y nos puede resolver muchas dudas. Yo sí que quería empezar preguntándote, ¿realmente qué estructura se cree que tiene este asteroide?
Bueno, pues realmente, más allá de la forma que se ha derivado de las imágenes de radar y de las curvas de luz, pues realmente no se sabe a ciencia cierta, ¿no? No sabemos lo que nos vamos a encontrar. En las curvas de luz y en el radar se ha visto una forma así un poco ovalada, pero lo que vamos a ver en realidad, ya digo, hay muchísima incertidumbre, ¿no? Sobre qué tipo de asteroide vamos a poder ver ahora mismo. Yo creo que va a ser una sorpresa para todo el mundo, ¿no? De hecho, esta tarde en el stream del grupo de ciencias planetarias de la Universidad de Alicante, bueno, la gente han preguntado que qué forma la gente espera que tenga Dimorphos, ¿no? Y la gente ha dicho formas de muchísimos tipos. Y seguramente eso vaya a venir condicionado también por qué tipo de asteroide nos vamos a encontrar. Si es un trozo de Didymos o si realmente es un grupo también de rubble pile o si es otra cosa totalmente diferente. Yo creo que eso también es un poco lo que le añade un poco de emoción a la misión, ¿no? Esa parte de incertidumbre sobre exactamente cuál es el cuerpo que nos vamos a encontrar. Y bueno, pues de momento yo creo que tenemos que esperar un poco. Todavía queda un pelín más de una hora y todavía ni siquiera hemos sido capaces de resolver la imagen de Dimorphos ni como un punto en las imágenes de Draco, ¿no? Y yo creo que ahora empieza un poco también los nervios para ver con qué sorpresa nos encontramos.
Que es curioso porque, y así ya metiendo temas... Ay, ya se te ve medio, ¿eh? Te he cogido la foto de perfil de Twitter. Ahí para que se vea también tu arroba. Si queréis, si tenéis luego más preguntas, le podéis... seguro que no se va a perder este evento, o sea que estará por Twitter, también le podéis preguntar por allí y obviamente seguirle. Sí que es cierto que o sea, yo también he estado en ese directo de inicio, estaba bastante interesante. Y realmente es muy difícil saber a ciencia cierta qué va a pasar, porque, o sea, hay modelos, pero claro, nunca se ha probado, es la primera vez.
Claro, hay modelos incluso de colisiones sobre asteroides de tipo esto de rubble pile, ¿no? De esto que son muchos fragmentos que van solamente viajando por el espacio por efecto de la gravedad, ¿no? Que a veces nos parecen bloques monolíticos porque hay tanto regolito, hay tanto polvo que hace como una capa así un poco superficial y nos da la impresión de que son solamente un bloque, ¿no? Entonces, claro, ¿qué va a ocurrir, ¿no? Con el impacto, ¿no? Tenemos que ver que es un impacto a muy alta velocidad, son más de 6 kilómetros por segundo, pero bueno, hemos visto también que muchas veces absorben muy bien el impacto este tipo de cuerpos, ¿no? Hemos visto que, por ejemplo, cuando hemos visto Ryugu y Venus, que son asteroides de este tipo, los cráteres son como muy someros, ¿no? Vamos a ver por primera vez, yo creo que si los cráteres es que se forman directamente muy someros y porque absorbe de una manera determinada el impacto, o si realmente luego con el tiempo se van relajando los esfuerzos y esos cráteres que podían ser más profundos en un momento, poco a poco van perdiendo su forma, ¿no? Yo creo que la verdad es que es muy interesante, no solamente lo que ocurra hoy con la misión, sino también con la futura misión de ERA, ¿no? Para poder ver ya de primera mano cuál han sido los resultados, más allá de lo que nos puede aportar, sobre todo las imágenes de las cámaras Luke y Leia que van a bordo de Alicia Cube.
Por aquí, por el chat, Diego González nos dice que eso no es una sonda, sino el penalti que lanzó Sergio Ramos hace 7 años en los cuartos de la Champions contra el Bayern. puede ser.
Bueno, podría ser, eso es una cosa a la que tenemos que estar abiertos también, por supuesto.
Claro, porque si por ejemplo el asteroide tiene más porosidad o está más compacto, va a tener un resultado, o sea, el desvío que va a quedar de la órbita va a ser diferente a que fuese bastante macizo, ¿no?
Claro, y dependiendo de la cantidad de material que salga eyectado, por ejemplo, también, ¿no? Hay muchos factores ahora mismo en juego. Por eso lo de la incertidumbre. No sabemos cuál va a ser realmente. Lo que se pretende es cambiar el periodo orbital de Dimorphos, cuánto va a poder ser, ¿no? Obviamente hay una ventana bastante grande en cuanto a lo que se pretende, a cuántos minutos o segundos se va a poder retrasar, que si no recuerdo mal, perdón, uno de los objetivos de la misión es que se retrase el periodo orbital o se cambie el periodo orbital de Dimorphos en unos 73 segundos. Eso como mínimo, ¿no?
Sí.
Así que vamos a ver si realmente con esta misión es suficiente o si realmente, viendo lo que ocurra hoy, podemos modelar con mucha menos incertidumbre cuál sería la próxima misión de defensa planetaria si es que se vuelve a probar, ¿no? Desde luego, por lo menos como primer experimento, yo creo que es una misión muy interesante y además hasta cierto punto muy sencilla, ¿no? Si pensamos, por ejemplo, hoy en DART tiene únicamente un instrumento, la cámara Draco, un instrumento científico, quiero decir, aparte del CubeSat que ya lanzó. Y eso, pues bueno, de algún modo lo hace una misión no extremadamente compleja, de esas que cuestan muchísimos años tener que construir y desarrollar grandes instrumentos. De hecho, incluso la cámara está basada en una de las cámaras que llevaba la sonda New Horizons, en LORRI. Entonces, bueno, pues yo creo que eso lo hace muy, muy, muy interesante desde el punto de vista de que si esta misión no tiene los resultados que se esperan, porque lo que nos encontramos es muy diferente a lo que creíamos, bueno, pues igual es el momento de repensar otra misión diferente. No verlo como un fracaso de ese objetivo concreto, sino, bueno, como un aprendizaje y una nueva oportunidad.
Total, realmente es eso, estás en la frontera del conocimiento y es curioso porque esta misión, como has comentado, solo tiene un instrumento científico, pero es muy pequeña, o sea, tiene un instrumento científico y es muy pequeña, pero para lanzarla al espacio se necesitó un Falcon 9 completito, o sea, no había ninguna otra carga en ese vuelo y dices, si un Falcon 9 puede lanzar no sé cuántas toneladas, ¿cómo va a lanzar? O sea, ¿cómo va a lanzar solo para una sonda de poco más de media tonelada? Pues resulta que es por la órbita que necesitaba coger, que tenía que ser muy cercana al ecuador para coger la velocidad y todo eso.
Claro, es que hay que tener en cuenta que una de las cosas que se van a ver en esta misión, ¿no?, es también un poco simular cómo serían esos impactos de pequeños cuerpos contra asteroides más grandes, y para eso se necesita una velocidad que a lo mejor de otra manera, con un medio de propulsión mucho menos, bueno, con muchísima menos delta V se podría conseguir, ¿no? Es verdad que la sonda DART creo que con combustible pesa como unos 600 y algo de kilos, ¿no? Que es relativamente poco para un Falcon 9 viendo todo lo que es capaz de lanzar, pero bueno, a veces el factor velocidad en algo como esto, porque en realidad esta misión es un impactador cinético, lo que se trata de transferir la energía máxima posible o una energía correspondiente para mover o desplazar el periodo orbital de un cuerpo, y para eso necesitas obviamente moverte en un umbral de velocidades, y a veces no tienes más remedio que usar un cohete pues algo más grande de lo que hubieses usado para lanzar a órbita baja una misión de este peso.
Sí, de hecho, un pequeño apunte, queda menos de una hora ya para este impacto de la sonda DART. Y sobre la misión y sobre la geología, ¿qué crees que con el impacto vosotros los geólogos podéis aprender?
Bueno, yo creo que sobre todo vamos a aprender mucho sobre el comportamiento de estos cuerpos tan interesantes, ¿no? Hasta hace no muchos años costaba imaginarse que los asteroides que pudiese haber asteroides formados prácticamente por un montón de rocas juntas y de polvo que viaja por el espacio, ¿no? Vamos a poder aprender mucho sobre su comportamiento, eso es fundamental, y espero que hoy porque como si no lo sabéis os lo cuento, entre otras cosas va a haber muchos telescopios apuntando. Y el hecho de que haya muchos telescopios apuntando, entre ellos el James Webb, igual nos permiten conseguir un espectro de cierta calidad del penacho de materiales que salga despedido, ¿no? Y eso sería muy bueno para poder conocer la composición. Hoy en día la composición de los asteroides la sabemos a grandes rasgos por varias cosas, ¿no? Primera, porque hemos hecho una clasificación de asteroides en base a su espectro. Otra, porque tenemos en la Tierra meteoritos que pueden corresponderse con esos espectros. Pero claro, también falta lo que llamamos el ground truth, que es poder tocarlo y poder verlo. Bueno, pues igual con este experimento también aprendemos un poco, ¿no? Y bueno, tenemos que entender que las amenazas planetarias a las que nos enfrentamos no solamente son asteroides de 11 kilómetros que caen en el Golfo de México, ¿no? En la península de Yucatán y son totalmente destructores porque son gigantes, ¿no? Impactos gigantes, sino que puede haber otro tipo de eventos que pueden ser de un tamaño mucho más moderado, quizás 10 o 100 veces más pequeños, y sin embargo pueden también causar una gran destrucción, ¿no? Yo creo que todos tenemos que pensar, por ejemplo, en Chelyabinsk, que fue en el año 2013, que fue un evento, yo no diría que casi de impacto, ¿no? Fue un evento en el que hubo una explosión
Explotó a 10 kilómetros.
En la atmósfera y bueno, generó una gran destrucción. Pues imaginemos que nos encontramos una amenaza a tiempo de este tipo, desviarla sería muy importante, pero para eso tenemos que también saber su comportamiento. ¿Cuál es la verdadera cohesión de ese cuerpo y de todas las rocas que viajan con él, ¿no? O si es un cuerpo monolítico, la cohesión nos imaginamos que es un poco más alta, ¿no? Pero bueno, todas esas cosas a veces, por desgracia, hay que verlas experimentalmente. Y bueno, hoy yo creo que es una buena oportunidad desde el punto de vista de la geología, porque a veces también vemos, cuando uno repasa, ¿no?, los asteroides, se da cuenta de que a veces ha visto asteroides en el espacio casi desmontándose, ¿no? Porque empiezan a girar muy rápidamente y tienen tan poca cohesión más allá de la gravedad que acaban girando muy rápido y acaban deshaciéndose en el espacio, ¿no? Y eso lo hemos llegado a ver. Y bueno, pues yo creo que es una oportunidad un poco muy interesante para poder conocer mejor estos asteroides y bueno, todos esos fenómenos, estudiar la cohesión sobre todo, para poder mejorar nuestros modelos y bueno, a ver qué pasa, ¿no? Y a ver cómo nos sorprende. Yo creo que muchas veces estas misiones tienen mucho de sorpresa, de bueno, igual nos encontramos algo diferente a lo que habíamos previsto, o igual es algo de lo más normal y demasiado normal, ¿no? Pero en cualquier caso yo creo que vamos a tener muchísimos años de artículos, de nuevos modelos, que sobre todo, ya digo, va a ser la clave para la defensa espacial, y bueno, y de aprendizaje, que todas las misiones siempre son importantes para aprender algo nuevo.
Una pregunta. El asteroide al que vamos a visitar con DART no será el del Principito, ¿no?
Bueno, me imagino que no. No, el del Principito. ¿Te refieres al pequeño del que da vueltas?
Creo que sí. Era B600 algo o algo así.
Sí, bueno, pero bueno, pues yo creo que no, porque yo creo que fue descubierto este asteroide en 1995-96 Didymos, o sea que es un asteroide muy reciente. Es un asteroide, pero bueno, por la forma, también, fíjate, una cosa muy curiosa, por el modelo de forma que tenemos de Didymos, yo creo que se presta mucho, bueno, ahora lo veremos en persona, ¿no? Pero por la forma, por el modelo que se ha hecho, sí que parece un poco el del Principito, en eso te voy a engañar, ¿eh? Se parece bastante.
Sí, es que me he acordado y digo, vivía en un asteroide. No le vayamos a romper la casa.
No, de hecho, la forma de que se ha derivado de radar y de curva de luz, yo cuando la veo digo, tengo ganas de ver este asteroide de cerca porque me recuerda en cierta manera a Ryugu y a Venus, ¿no? Esa forma casi con un ecuador, con una banda ecuatorial muy marcada, casi con forma, a lo mejor, no tanto de diamante, pero sí también con esa forma tan característica que tienen esos dos asteroides. Y bueno, igual luego la forma no se parece tanto, o sea que tenemos que estar aquí atentos a la sorpresa. Y de hecho, bueno, ahora mismo creo que no sé si empieza a resolverse ya un poco más.
No, todavía sigue siendo un punto.
Sí, bueno, pero ya le veo más píxeles, ya veo
Sí,
algo,
sí,
ya veo algo más.
ya se ven más píxeles. Esto me recuerda mucho a la imagen de cuando se veía la primera Crew Dragon llegando a la ISS, que al principio era un puntito al fondo, al fondo, al fondo, y cada vez se hace más grande.
Claro.
Me recuerda mucho esta imagen.
Bueno, estamos a 19.000 kilómetros, 500 de Dimorphos. O sea, ahora mismo, en este mismo momento, tengo aquí la tabla de datos y si no me equivoco, o sea que bueno, que ya estamos bastante más cerca, ¿eh? Se va acercando mucho el momento del impacto.
Para los que no sepáis, la imagen que justo tenéis en pantalla son los datos a tiempo real que están llegando de la sonda, y ese puntito blanco que hay en la pantalla es de momento el sistema binario. Que de hecho, no sé si conoces que el sistema para diferenciar los distintos asteroides es un sistema creado inicialmente para la defensa antimisiles.
Sí, eso había leído, me resulta muy curioso porque sobre todo en las últimas décadas también se ha mejorado mucho el tema de la navegación espacial y sobre todo la navegación estelar. Pero bueno, me imagino que también a la velocidad a la que viaja, hoy estamos viendo una misión muy rápida, mucho más de la que estamos acostumbrados, ¿no? No es lo mismo acercarse a Júpiter que acercarse a 6 kilómetros por segundo a un asteroide que es mucho más pequeño y empieza a resolverse mucho más tarde. Entonces me imagino que se necesita algo más, una técnica mucho mejor.
Sí, realmente sí que funciona por navegación a través de estrellas, pero justo es en el último momento, bueno, a partir ya de este momento que la nave coge el control automático del vuelo, cuando se activa este sistema que es el Smart Nav, que es curioso porque al final ves como aplicaciones que inicialmente estaban pensadas para el ámbito militar, para el ámbito de defensa, al final han acabado perfectamente funcionando en el campo espacial, y al revés, que también ha sucedido muchas veces.
Claro, mira, ahora mismo, por ejemplo, el tiempo de ida y vuelta de una señal está con dar desde casi un minuto y poco más, ¿no? Tú imagínate pilotar una imagen a una velocidad tan grande y desde la Tierra, ¿no? Con ese retraso. La verdad es que es muy difícil. Y claro, bueno, tenemos que entender que la distancia son 11 millones de kilómetros, o sea que está muy lejos en cuanto a escala humana. Si pensamos que la Luna está solamente a 380.000 kilómetros, a mí esto me parece lejísimos, aunque no sea obviamente un espacio muy profundo.
Sí, realmente la Luna está a 1,5 segundos a la velocidad de la luz.
Claro.
Creo que es contando las latencias de los sistemas y tal. Y los aterrizajes se hacen automáticamente, no hay nadie ahí con un joystick en tierra controlando. Así que cuando ya hablamos de millones de kilómetros, sí o
Claro,
sí tiene que ser automático.
todo se complica mucho más, ¿no? La latencia al final es fundamental. Siempre el ejemplo a lo mejor más clásico son los 7 minutos de terror de la entrada a la atmósfera de Marte, ¿no? Y el aterrizaje. ¿Quién va a manejar con 10 minutos de retraso una misión? Es imposible. Tenemos que confiar en los sistemas automáticos. Por suerte, que hoy en día son muy buenos siempre. No tenemos otra alternativa hasta que no podamos ir más cerca con las misiones robóticas, desde luego.
Por aquí antes estaban comentando algo sobre... Ah, sí, que quería comentar. Ahora mismo lo que la NASA está explicando es más o menos lo que estamos explicando nosotros, pero lo explican en inglés y luego están mezclando cosas de que la NASA es muy buena agencia espacial, ya sabéis. Nosotros vemos todo de manera más objetiva. Y otra pregunta que estaba por el chat es si sería o no sería peligroso este satélite remotamente para la Tierra.
No, desde luego, después del impacto no sería peligroso. En todo caso, es cierto que una vez que ocurra el impacto, el mayor movimiento se lo va a llevar el satélite, se lo va a llevar Dimorphos, pero también va a cambiar un poco la órbita de Didymos y bueno, o del sistema binario en general, ¿no? Porque al final al transferir esa masa un poco más fuera, un poco más dentro, va a alterar un poco el periodo orbital, pero en ningún caso va a suponer ningún problema porque estamos hablando de un cambio realmente mínimo en la órbita. Creo que ya se ve Dimorphos en las imágenes. Veo 2 puntos ahora mismo. No sé si puedes...
esto no se va a ver en el directo, pero sí se puede empezar a apreciar un segundo punto un poquito a la derecha a la derecha y arriba, ¿no?
Sí, arriba a la derecha, exactamente.
Por aquí, más o menos. Ah, claro. Sí, sí, ven el ratón. Pues por ahí, justo donde está la puntita del ratón, es donde se empieza a apreciar ese pequeño puntito bueno, donde vamos a hacer Diana. Que es muy curioso también el nombre de la misión. Dardo, y realmente
Sí, sí.
vas a hacer Diana.
Claro, realmente es una diana y además una diana muy complicada porque a la velocidad a la que viaja la misión, cualquier mínimo cambio, cualquier mínimo movimiento y sobre todo estamos hablando de cuerpos tan pequeños que salirse del centro de la diana es muy fácil. O sea que a mí esto me da un poco de miedo, la verdad.
Sí, sí. Sí, yo más miedo que hay personas que dicen, buah, tengo miedo de que desvíe la órbita. No, yo, si hay que tener miedo de algo es de que se lance la misión y que luego no le dé y pase a 10 metros a la derecha, que, bueno, pues también se aprenderían cosas porque esta misión es cierto que los propulsores utilizan Next-C, que es un nuevo tipo de propulsor. Los paneles solares también es demostrador tecnológico, que son estos enrollables. Entonces, no hubiese sido en vano la misión, pero bueno, no se hubiese completado el objetivo principal.
Claro, pase lo que pase, la misión no, yo no la considero en vano, ¿no? Obviamente, si cumple los 4 objetivos, maravilloso, ¿no? Pero tenemos que tener en cuenta que cualquier cambio, cualquier movimiento, cualquier cosa que no se tenga que no se tenga en cuenta puede ocurrir. De todas formas, obviamente las simulaciones en la Tierra habrán hecho miles y miles de simulaciones con estos 2 puntitos para como ya lo que queda tiene que navegar solo para que den el centro, ¿no? Yo a veces la verdad es que reconozco que tengo mucho miedo, ¿no? Porque son misiones, pues eso, muy interesantes. Todas las misiones espaciales son muy caras, cuestan muchísimo, no solamente muchísimo dinero, sino muchísimo tiempo. El mandar una misión al espacio, muchísimos años de preparación, de montaje, bueno, todas las trabas burocráticas para que tu misión salga elegida. Claro, si luego falla, pues obviamente es un palo, ¿no? Pero yo creo que vamos a confiar que seguro que lo van a lograr al 100% el objetivo. Y además es que vamos a conseguir muchísimos datos. El hecho de que haya tantas, ahora mismo, redes de telescopios en la Tierra observando y apuntando, esperando ver ese cambio de brillo. El J-Web también está, creo que el VLT, o sea que hay un montón de ojos.
Todos los ojos posibles están apuntando a este evento porque es único. De hecho, las antenas de radio, he leído por Twitter que hay radioaficionados que quieren intentar captar de esto de DART, la señal de DART. A mí eso ya me parece palabras mayores.
Bueno, yo creo que creo que alguna vez hay una antena en una ciudad alemana, en Bochum, que yo creo que han usado más de una vez los radioaficionados para algunas misiones, ¿eh? Y creo que bastante recientemente, creo que con algunas, incluso creo que han llegado a detectar señales de las misiones chinas que están en Marte.
Pues
eso... y con eso son capaces de detectar si ha habido un cambio de órbita, si han usado los propulsores, todo ese tipo de cosas, ¿no? Midiendo el efecto Doppler.
Yo me acuerdo, bueno, desde que hackearon a SpaceX, no sé si hackearon la señal de SpaceX y se filtró una cámara del tanque de combustible. Una de esas que tienen para los ingenieros y tal, en el lanzamiento siguiente ya estaba codificada.
Claro.
Porque claro, no estaba cifrada. Y luego a los chinos también se les hackeó varias veces la Chang'e 5, la señal para obtener imágenes y vídeos.
Claro, es algo que a nosotros nos parece, no sé cómo decirlo, hasta cierto punto muchas veces son cosas rutinarias, son telemetrías, son pues las imágenes que puedan ir más o menos codificadas, pero claro, una agencia espacial nunca quiere dejar a que cualquiera pueda acceder a sus sistemas, ¿no? Ya no solamente por recibir, sino por... Y si somos capaces de descubrir el código para enviar una señal y hacer algo mal, ¿no? Yo creo que, no sé si los oyentes nos recordarán, que hace unos años se intentó recuperar una sonda, creo que no sé, de los años 70 o de los 80, y se intentó volver a activar sus propulsores y fue gracias al movimiento hacker y al movimiento maker. O sea, que se ha intentado más de una vez, ¿no? Y además con permiso de la NASA. Pero bueno, no tuvo éxito porque por lo visto los propulsores no funcionaban o habría alguna fuga o cualquier cosa que complicaba mucho la cosa. Pero bueno, es normal que todo el mundo intente guardar sus secretos de alguna manera.
Sí, luego están los ingenieros de la NASA que tienen que intentar descifrar lo que hicieron trabajadores de no sé qué año cuando estaban programando la Voyager, que ahora han llegado al cargo y la Voyager sigue funcionando. No saben qué pasa, pero
Eso es durísimo, ¿eh?
tienen que repararlo y ellos no han conocido ese sistema de programación ni nada y se tienen que poner a estudiarlo.
Claro, es que estamos hablando de que todo ha cambiado muchísimo. Estamos hablando de 50 años de exploración espacial así más dura. Y claro, todo ha cambiado radicalmente. De hecho, no hace falta irnos tan lejos. Fijaos que la Mars Express, la sonda, ha recibido una actualización en este verano para mejorar su sistema de radar y se ha programado ya en entornos de programación mucho más modernos, que son los que han permitido el poder optimizar el código tanto como para enviarlo a la Mars Express y que obviamente pueda funcionar de otra manera distinta a la que estaba previsto. O sea que es increíble un poco cómo cambian las cosas, incluso para misiones que están muy activas y que no han pasado tantos años, que estamos hablando de apenas a lo mejor la Mars Express 20 años. No lo recuerdo. Sí, puede ser.
Yo creo que no estaba vivo en el momento del lanzamiento.
Pues incluso que se ha tenido que cambiar de entornos de programación, porque obviamente eso ya es mucho más moderno y sí que se puede.
Sí, 2003, sí que estaba vivo.
2003.
Tenía un año.
Pues fíjate para que incluso en algo tan reciente se ha podido cambiar mucho, ¿no? Pero claro, las Voyager son mucho más antiguas y obviamente no permiten esos entornos de programación tan modernos. Pero, ¿qué pasará? Imaginemos que la Mars Express dura 20 años más. Sabremos programarla y podremos programarla. Habrán manuales para poder seguir haciendo el mantenimiento.
Hombre, espero que en 20 años podamos ir y enchufarle el USB.
Espero.
Por aquí preguntan por qué la imagen se ve tan baja calidad, la imagen de DART, de la cámara Draco.
Pues realmente no lo sé, pero yo creo que es porque está muy lejos todavía.
Bueno, al final son dos factores, que está muy lejos y que realmente no es una cámara tan precisa como igual la que tienes en el iPhone 14.
También creo que es como la Low-Rig, no sé si tiene 2048 por 2048 píxeles, algo así, que no es una cámara de 50 megapíxeles, es algo mucho más comedido, pero tenemos que entender que la sonda transmite a una velocidad máxima de 3 megabits por segundo. Antes comentaba yo que para bajarse una imagen de un teléfono móvil normal, un JPG de 5 megas tardaría casi 14 segundos. Pero por eso, pues no se puede, obviamente. La última imagen seguramente, de hecho, va a ser unos 17 segundos antes del impacto, porque es que no le va a dar tiempo a transmitir la siguiente imagen. Va a impactar directamente y se va a acabar. Y eso también tenemos que tenerlo en cuenta, ¿no? Hay varios factores que restringen mucho qué cantidad de imágenes y qué calidad de imágenes vamos a poder ver. El primero es el sensor, que bueno, que en Plutón vimos que funciona bastante bien la cámara Low-Rig, entonces, bueno, podemos confiar en que esa calidad está bien, pero claro, tenemos que entender que ahora mismo hay otro factor que apremia mucho, que es el impacto, ¿no? Y bueno, vamos a ver qué tal y cómo son las últimas imágenes. Yo tengo muchísimas ganas ya de que llegue ese momento y bueno, ya queda poco.
Por lo que he estado leyendo, se prevé que la última imagen de todas se vea el asteroide completo.
Pues probablemente porque, bueno, no sé a qué distancia la hará, pero si es en los últimos 17 segundos, a 6,6 kilómetros por segundo, pues probablemente si no se ve el asteroide completo se verá ya un trozo relativamente cercano. Vamos a ver cómo es. Yo tenía ganas de ver un poco mejor la superficie, ¿no? Ver si realmente se puede afinar un poco más. Sí, exactamente. Algo así, ¿no? Por lo menos que podamos afinar claramente o distinguir claramente qué tipo de asteroide es en la imagen. Y si no, bueno, pues lo dejaremos a los datos de después, ¿no? Pero por tener un poco más de detalles sobre el propio asteroide. Dimorphos seguramente lo veamos bastante o relativamente bien conforme nos vayamos acercando, pero también bastante más grande. Pero bueno, Didymos todavía le queda un poco. Dimorphos, perdón, le queda un poco.
Sí, Didymos es el grande.
Es
Por,
grande, sí.
por aquí estaban diciendo una cosa por el chat y es cierto. Los directos de la NASA son a 720.
Sí.
La NASA es capaz de estampar sondas contra un asteroide, es capaz de enviar al Perseverance y hacer maniobras espectaculares en Marte, pero no es capaz de emitir a 1080, 60 FPS.
Es raro, ¿no? Porque hasta SpaceX está emitiendo ahora en 4K los lanzamientos,
Sí,
creo.
a partir de Artemis, bueno, ya de hecho para Artemis está preparado para emitir a 4K, pero es un poco raro que la NASA, que dices, es tecnología por todos lados, emitan a eso, a 720 cuando podrían hacerlo a 1080.
Claro, efectivamente, por lo menos 1080, ¿no? Que sería una... Sobre todo yo ahora, por ejemplo, tengo el monitor grande que es de 4K y se ve muy mal realmente. Pero bueno, al final también yo creo que aprenderán un poco de SpaceX, ¿no? Que al final el marketing, bueno, espero que en algún momento aprendan, aunque suelen hacer bastantes cosas chulas, pero le falta un pelín más de marketing para que la gente pueda verlo mejor y pueda disfrutarlo no solamente en el ordenador, sino también en una televisión, ¿no? Si tú pones un stream de 720 en una tele moderna, pues se ve un poco regulín. De todas formas, las fotos que estoy viendo yo ahora, estoy viendo el stream en una pantalla normal y todavía no tienen calidad suficiente. Vamos a seguir viendo un ratín el punto gordo y el punto pequeño. O sea, que nadie se piense que va a haber resuelto ya el sistema binario con sus detalles, ¿no? De los asteroides. Todavía quedan unos minutos para poder empezar a distinguir algunas cosas más. Porque realmente están lejos. O sea, que es que no es una cosa que está cerca.
Por aquí preguntan a qué distancia está el asteroide de la Tierra. Eran más de 10 millones, creo, ¿no?
Sí,
Por
son
aquí-
unos 11
sí,
millones de kilómetros.
Por aquí ponen 11 millones también.
Sí, 11,3 creo que millones de kilómetros ahora mismo.
Sí, al lado.
Sí, está bueno,
Bueno,
cerquita.
solo hay que compararlo. Está mucho más lejos que el James Webb, y el James Webb ya nos parece que está lejos, pero está mucho más cerca que Marte. Solo hay que... todo depende del punto de referencia en el que te bases para decir si está lejos o está cerca.
Bueno, mira, el J-Web está transmitiendo a la antena número 54 de Madrid a 28 megabits por segundo.
Cierto,
O sea,
cierto,
sí.
cierto. Y bueno, Madrid está... ¿Qué se sale?
Sí.
Dart se queda todavía con Canberra.
Sí, Dart se va a quedar con Canberra, yo creo que porque me hacía mucha ilusión el poder fotografiar desde la Tierra el impacto, pero resulta que para los que estamos en el hemisferio norte, pero relativamente lejos del Ecuador, el asteroide está muy bajo o incluso bajo del horizonte, ¿no? Entonces no se
Sí.
puede, es una pena.
No en ese aspecto no hemos tenido suerte. De hecho, el punto del impacto va a ser justo enfrente de África. Entonces, para que la gente se haga una idea, más o menos por dónde estará, pero por la parte sur de África. Entonces, claro, desde España no se puede ver con un telescopio. Bueno, esperemos que algún aficionado que esté por allí, por África, y pueda a ver si... Para saber más o menos, o sea, porque podemos saber lo que capta un gran telescopio, pero también a mí me gusta ver lo que captan los telescopios más pequeños de aficionados, porque al final, no sé, me gustan más las fotos se les pone como más cariño.
Sí, bueno, yo creo que probablemente la gente que sepa hacer fotometría bien va a poder ver el cambio en la curva de luz, porque hoy en día pues tenemos cámaras muy sensibles, la gente que hace astrofotografía es una verdadera profesional muchas veces y sabe manejar las técnicas más modernas de una manera increíble y seguro que va a poder sacar por lo menos ese aumento de brillo seguramente que haya después de la colisión, ¿no? Yo creo que también es interesante ver hasta dónde los amateurs también van a poder hoy aportar esa información.
Sí, o sea, estamos expectantes. Y otro protagonista de esta misión será el satélite o CubeSat italiano LisaCube, que ya se separó de DART hace un tiempecito y que podrá captar cómo es ese material eyectado y si hay suerte, podrá ver el nuevo cráter.
Claro, bueno, a mí me parecía que fue ayer y se separó hace 15 días, o sea que bueno, va un poco rezagada con respecto a DART, pero al final lo que intenta es ver eso, ¿no? El momento en el que sale la esta despedida y poder caracterizar con un poco más de detalle el impacto. Vamos a ver qué imágenes salen del CubeSat. Ya hemos visto algunas de las imágenes que es capaz de hacer, que se publicaron en la página de DART, que las puede ver quien quiera en la página de DART, que hay una de las Pléyades y una de la Tierra, ¿no? Y yo creo que si funciona así de bien vamos a poder ver imágenes bastante buenas. Hemos visto tanto una imagen de luz, que es la cámara color, que es la de las Pléyades, y la imagen de la Tierra en blanco y negro, que es de la cámara Leia, y que es la que más tiempo además va a estar funcionando.
A mí me gusta mucho este concepto del CubeSat que acompaña al satélite, que también lo vamos a ver. Esperaba que lo viésemos antes, pero no va a ser el caso. También lo vamos a ver en la misión Artemis 1, que van 10 CubeSats acompañando bueno, no acompañando, sino que acompañan al SLS, pero a mitad de misión ya se separan de la segunda etapa, de la ICPS, y no van con la cápsula Orión. Pero me parece muy interesante ese concepto de pequeños mini satélites que hacen como una red, que te pueden ir a ayudar, que te pueden complementar las misiones y que te pueden dar muchas perspectivas que es mucho más difícil conseguir con... Bueno, no mucho más difícil, sino muchísimo más caro conseguir con otro tipo de satélites, ya que te permite eso, tener muchas cámaras de diferentes ángulos en diferentes posiciones y de manera simultánea.
Claro, ya vimos, por ejemplo, cuando se lanzó el Perseverance, que fue con 2 CubeSats, que se pensaba que para espacio profundo no iban a funcionar muy bien, porque bueno, el entorno de radiación es muy diferente al de órbita baja, y los paneles solares y las comunicaciones, obviamente, un CubeSat tiene una dimensión muy pequeña, no puedes poner una antena muy grande. Y sin embargo funcionaron bastante bien, ¿no? Yo creo que esa prueba de concepto fue todo un éxito, y realmente puede ser al final también una revolución, ¿no? Vamos a poder llevar muchas más misiones, aunque lleven menos instrumentos, llevarlas más lejos, probar cosas nuevas y totalmente diferentes, que aproximaciones que quizá parecieran muy radicales para una misión muy grande, pero que para una misión pequeña de pruebas y con un coste mucho más económico sí que se pueda plantear y que sí que se puede hacer, ¿no? Yo creo que eso también yo creo que eso va a ser también un cambio muy importante en los próximos años, ¿no? Que hasta dónde vamos a poder llegar con cosas relativamente pequeñas, tecnologías que antes se pensaban que bueno, eran muy poco resilientes en el espacio. Lo hemos visto también en el Ingenuity, ¿no? Que se decía, bueno, se va a mandar un procesador que no está preparado para el entorno de radiación, no sé cuánto, no sé qué.
Todavía me acuerdo. Primer vuelo, ¡buah! Ingenuity ha volado, espectacular, épico. Nadie pensaba que fuese posible. Ingenuity ahora, ya estamos preparando el vuelo número 33.
¡Qué aburrimiento!
Sí. O sea, Ingenuity ya es como cuando SpaceX lanza Starlink. O sea, SpaceX lanza... Ah, vale, otra vez, ¿no? Pero claro, luego te pones a pensar, a ver, ¿me estás diciendo que ha habido un bicho que ha volado 32 veces con éxito, que ha tenido algún que otro problemilla, que se ha arreglado con software y sigue ahí dando buenos resultados en Marte?
Claro, yo creo que hay una diferencia importante. Misiones grandes siempre van a tener que existir, porque hay pues instrumentos que tienen que ser grandes, ¿no? Un espectrómetro de masas, toda la instrumentación, por ejemplo, el carrusel del Perseverance solamente para llevar las muestras tiene que ser grande, porque es una mecánica muy grande, muy compleja y tal, pero para otras cosas más pequeñas, para dejar un instrumento pequeño en la superficie, una cámara o una pequeña estación meteorológica, cosas que sean relativamente pequeñas, o por ejemplo, una red de satélites meteorológicos en Marte que pudiese ser en CubeSat, ¿por qué no? También, ¿no? En un formato mucho más pequeño. Obviamente en Marte es un poco más problemático el poner satélites meteorológicos, pero bueno, podría funcionar. O cosas así que nos pueden parecer aproximaciones muy radicales, pero que bueno, por el coste sí que se pudieran por lo menos probar. En la Tierra ya están resultando una revolución. Aquí usamos CubeSat y hay satélites muy pequeños incluso para observación del planeta Tierra, ¿no? Porque hoy la tecnología de las cámaras ha mejorado muchísimo, se pueden tomar imágenes con cámaras mucho más pequeñas que no necesitan unos equipos de refrigeración tan grandes y las misiones tienen un coste mucho menor. Cuando se cae el satélite deja de funcionar o ya no se puede mantener en órbita, bueno, pues se sustituye por otro, no pasa nada porque no estamos lanzando una misión de 1000 kilos, sino una misión de 40 o de 50 kilos, que obviamente tiene un coste mucho menor.
Totalmente. De hecho, justo esto es ya como hay primicia. En unos días vamos a publicar aquí en el canal una entrevista con un consultor espacial a raíz de la World Space Week, que la Semana Mundial del Espacio es del 4 al día 11, del 4 al 11. Y estuvimos hablando sobre esto, sobre todo el New Space, sobre todas las oportunidades, tanto en estos CubeSats como las oportunidades para futuras empresas a partir de esa información y que se viene toda una revolución, tanto a nivel de la Tierra como a nivel de exploración.
Claro, al final, siempre cuando pensamos en satélites de observación de la Tierra, que yo siempre hablo de eso porque lo que más cercano me resulta, ¿no? Siempre pensamos en satélites grandes, estamos pensando en satélites como el Landsat o el Meteosat, por poner un ejemplo de satélite del tiempo.
Con autobuses, pensamos en
Sí,
autobuses.
exactamente, pensamos en una cosa realmente gigantesca. Bueno, pues hay empresas que hoy en día hacen satélites de observación de la Tierra que son mucho más pequeños, que sí que es cierto que no están en órbita geoestacionaria, que están en órbitas bajas, tal, pero que son capaces incluso de hacer vídeo. Yo hace unos años, cuando la primera vez que vi un vídeo desde el espacio de un satélite de estos, yo no me lo creía. Digo, ¿cómo van a estar grabando vídeos del espacio? Pero ¿cómo gira el satélite tan bien, ¿no? Con esa precisión para poder grabar un punto. Y un satélite que no es militar, pues si fuera un satélite militar te sorprende un poco menos. Pero un satélite civil ya es sorprendente.
Las fotografías, justo, mira, ahora que se cumple un año y que me acuerdo que estuvimos hablando bastante, que sacaba Maxar o Planet con esas imágenes oblicuas del volcán de La Palma.
Claro, pues por ejemplo, exactamente. Eso no deja de ser una maravilla, ¿no? Porque además de que la cobertura puede ser mucho más habitual que, por ejemplo, los satélites de media resolución como Landsat o como los de Copernicus, como los satélites Sentinel. Claro, tú puedes tener yo qué sé, como un montón de estos mini satélites que puedan estar todos los días, incluso haciendo varios pases sobre el mismo punto de la Tierra, ¿no? Y eso te permite una cobertura espacial y temporal mucho más grande que te permite también cuantificar procesos que ocurren en la Tierra, pues ya sea desde inundaciones hasta cambios meteorológicos o de ocupación del territorio o de cualquier cosa, ¿no? Yo creo que eso es importante que lo tengamos en cuenta, ¿no? Que esa verdadera revolución a lo mejor no la notamos ahora, pero que quizá en una década estemos hablando bueno, de una economía también muy basada en el espacio porque también nos interesa ver las cosas desde ahí arriba.
Ahora sí que ya se empieza a distinguir bastante mejor el segundo, bueno, nuestra Diana. Se ve muy bien Didymos, pero Dimorphos ya se empieza a ver bastante mejor. Es un punto un poquito más grande, ya han pasado de ser 2 píxeles a ser 4 en las
Claro.
imágenes.
Voy a ver a cuántos kilómetros está ya porque ya tiene que estar muy cerca.
Muy cerca, porque estamos a 26 minutos, creo que
A
es
ver,
24 minutos y 48 segundos.
pues ahora mismo se encuentra a 9.000 kilómetros, 9.200 me sale a mí ahora mismo.
Eso es un vuelo de avión, ¿eh?
Sí, sí.
Está a la distancia de un vuelo de avión. Esto ya está aquí al lado.
Ya estoy nervioso yo a ver dónde está la nave.
Sí, sí.
Sí, ya se ve bastante mejor, sí. Ya parece. La forma me parece todavía un poco rara, pero yo creo que hay un poco de suavizado probablemente porque la imagen sea más pequeña, ¿no?
Sí.
Entonces todavía no estemos viéndolo.
Estará rescalada, seguramente.
Sí, seguramente. Y si están usando algún cubic smoother o alguna cosa de esas, todavía se ve un poco raro, ¿no? Pero yo creo que, bueno, en unos minutos vamos a ver todavía mucho mejor el sistema, ¿no? O sea que, bueno, me imagino que en algún momento llegará a cubrir toda la imagen, o sea que lo vamos a ver muy bien.
Sí. Si tenéis alguna pregunta sobre esta misión, sobre temas más concretos de la misión de geología, esta vez tenemos oportunidad de preguntarle a un geólogo, entonces tenemos a quien preguntar y que nos diga bien, porque yo te puedo decir cosas de bueno, se lanzó con el Falcon 9 y el perfil de la misión, pero de geología la verdad es que nunca ha estado muy, muy puesto.
A ver si hay alguna novedad. No hay novedades por aquí.
No, lo único eso, que se acaba de acabar la segunda ronda de checks en T-30 minutos de los controladores de tierra de la misión y los sistemas ya han fijado al sistema binario de satélites y ya se dirigen hacia él.
Ah, vale, perfecto, pues nada.
Pues hacía tiempo que quería que vinieses a un directo Era de lanzamiento, pero esto también vale.
Bueno, el cohete va lanzado, o sea que va también bastante rápido.
Va más rápido que velocidad orbital, ¿eh?
Sí, claro.
Entonces,
Estamos hablando de 6,6 kilómetros por segundo. Va
mm,
muy rápido.
depende qué cohete y qué órbita vas más rápido. O sea, el Falcon 9 no llega a tanta velocidad. Necesita de la segunda etapa. Pues, de hecho, me acuerdo que dije, estaría bien quedar contigo para una misión donde hubiese geología de por medio. Y dije, bueno, me acordé cuando se lanzó DART, digo, hubiese estado bien que hubiese venido, pero también te digo, el lanzamiento de DART fue a una hora intempestiva por la mañana.
A veces pasa. Los lanzamientos son cuando tienen que ser. Eso
Sí,
no
sí.
no tiene ni
Pero,
vuelta de hoja.
y estaba esperando a una misión lunar o algo así que se pudiese aprovechar la ocasión, pero no, se ha ido retrasando todo, pero bueno, hemos organizado este directo en 10 minutos.
Bueno, desde luego yo del SLS no me fío ya. Eso no puede ser. No de tanto retraso ya no puedo con mi cuerpo.
Yo tampoco.
Llevamos ya, bueno, no sé, al final, bueno, noviembre se va, ¿no? El SLS con la Artemisa 1. Es que, bueno, es un poco de sufrimiento también, todos los problemas que tuvo con la fuga de hidrógeno y si ahora le sumamos un huracán, pues bueno, ya creo que lo comentaba el otro día con Daniel Marín, son las 7 plagas, básicamente. Veremos a ver si, bueno, no pasa nada más después del rollout y de que vuelva. Así que vamos a ver.
Por aquí preguntan si el CubeSat tiene instrumentos para analizar el polvo o no. Espectrómetro no tiene, ¿no? La cámara.
No, que yo sepa solamente tiene las dos cámaras que son Leia y Luke, una Leia en blanco y negro y Luke la cámara en color, no tiene nada más.
¿Y es similar a Hayabusa o Sirius Rex, porque dice otros asteroides, o es bastante distinto este?
¿En qué sentido?
Supongo que es morfología, composición.
Bueno, en composición los asteroides, otros eran asteroides de tipo C, asteroides un poco más primitivos, y ahora estamos seguramente ante un asteroide de tipo rocoso, ¿no? De tipo silíceo, que además tiene un color un poco, vamos a ver, creo que un color un poco más claro, un albedo un poco más alto y con una composición bastante diferente. También por eso la importancia, ¿no? de elegir este asteroide es otro tipo de composición, más cambiada, más evolucionada desde el principio del sistema solar. Y bueno, para aprovechar también para ver un poco de cerca cómo es este sistema, ¿no? Ya sabemos cómo se comporta también un asteroide de tipo Russell-Pyle ante un impacto, porque, bueno, la sonda, la Osiris Rex, aunque fuese poco, al posarse algo hizo, ¿no? Bueno, ahora nos toca ver también si un asteroide de tipo S se comporta de una manera diferente o se comporta igual. Yo creo que va a ser muy... Eso, que yo creo que vamos a aprender bastante, porque también tenemos que tener en cuenta que nuestro sistema solar a veces no nos lo parece, pero nuestro sistema solar es súper diverso en composiciones, en tipos de cuerpos. Unos son más compactos, otros son menos, otros están totalmente fragmentados. En fin, que eso siempre le añade un grado de dificultad a la hora de planificar una misión y en este caso, por ejemplo, una misión de defensa planetaria.
Por aquí también preguntan sobre la composición y a raíz de lo que acabas de decir, que es un asteroide más evolucionado, ¿qué materiales podemos encontrar? Porque has mencionado el silicio, ¿podemos encontrar algún otro tipo de material o así? Y luego, ¿podrían ser este tipo de asteroides usados para minería espacial o no?
Bueno, al final, a ver cómo lo explico, ¿no? Al final, todos los asteroides pueden ser usados para minería espacial, depende del recurso que nos interese, ¿no? Por ejemplo, de los asteroides de tipo carbonoso, ¿qué nos interesa? Pues muchas veces el contenido de elementos volátiles, ¿no? Por ejemplo, el agua, que podríamos sacar, digamos, cociendo el asteroide. ¿Qué podríamos sacar en los de tipo S? Pues podríamos sacar seguramente pues, magnesio, por ejemplo, podríamos sacar platino, podríamos sacar algunas tierras raras, podríamos sacar incluso algo de hierro, porque muchas veces cuando pensamos en asteroides, sobre todo para la minería del metal, pensamos muchas veces en los asteroides de tipo metálico, pero por ejemplo, un asteroide metálico que sea monolítico, yo no sabría, por ejemplo, cómo extraer, por ejemplo, estoy pensando, por ejemplo, en algo como Psique, ¿no? Que pensamos que es un asteroide, bueno, no tan metálico como antes, pero bueno, algo más monolítico, ¿no? Algo duro. ¿Cómo podríamos extraer, por ejemplo, el hierro de ahí? Yo la verdad es que no lo sé. Sin embargo, en otro tipo de asteroides, como por ejemplo los de tipo S, que son rocosos, pero eso, que pueden contener algunos metales, ya digo, pues pueden contener platino, pueden contener magnesio, pueden contener hierro, oro, pues procesándolo como procesamos en la Tierra la minería normal, las rocas comunes, podríamos también sacar elementos muy, muy importantes, ¿no? Todavía queda también mucho por saber en cuanto a la cantidad de elementos, sobre todo, no solamente los elementos comunes en nuestro planeta, sino esos elementos que en la corteza de la Tierra son bastante más raros. Cuánto contienen los asteroides, ¿no? Y para eso luego todavía nos faltan algunas misiones que sean capaces de caracterizar mejor los distintos tipos de asteroides, ver si vienen de una familia en común y luego pues intentar unir todos esos datos y modelar mucho mejor las abundancias de estos elementos. Para eso yo creo que todavía falta alguna década. Todavía creo que nos queda un pelín.
Y por aquí preguntan si los geólogos tenéis buenas herramientas para determinar la composición de un asteroide, bueno, o un satélite, y si las tenéis, cómo funcionan más o menos.
Vamos a ver, tenemos herramientas. La herramienta principal que manejamos hoy en día es el espectro de la luz del asteroide, los que no podemos tocar, obviamente. Eso dificulta muchísimo. ¿Por qué? Porque nosotros vemos el espectro de la superficie, pero muchas veces la superficie puede llevar polvo, por ejemplo, que puede estar cubierto, como pasa en Marte, ¿no? En Marte ocurre una cosa y es que Marte todo está cubierto de un polvo de color rojo, absolutamente toda la superficie. Eso nos hace que la señal de la roca que hay debajo, nosotros o no podamos verla bien o directamente no podamos verla. A veces con los asteroides pasa cosas parecidas. ¿Cuál es la mejor manera de poder saber qué composición y las proporciones de los distintos elementos y minerales? Muchas veces es yendo, ¿no? Es pudiendo saborear, por decirlo de una manera sencilla, el asteroide. Pero bueno, yo creo que todavía también hace falta un poco una revolución en la propulsión en cuanto a misiones espaciales que nos permitan el poder llegar un poco más lejos y el poder mandar más misiones para que efectivamente podamos caracterizar mejor la composición de estos.
Cuando habláis de hacerle un espectro, lo que tengo entendido que sería, al menos es como se hace en las atmósferas de los planetas, es que hacéis el espectro del Sol y luego le restáis el espectro de la estrella, ¿no?
Bueno, en este caso, en vez de hacerlo a través del asteroide, como la atmósfera, lo que hacemos es la luz reflejada.
O sea, sí, pero le tenéis que quitar el espectro, o sea, le tenéis como que restar el espectro de la estrella, ¿o no?
Sí, a veces se tiene que restar, depende de cómo sea el albedo, se tiene que restar o no. Sí. Vamos a ver, hay señales que siempre tú tienes que quitar, ¿no? Si un asteroide, por ejemplo, o un cometa es de un color muy blanco, muy blanco, muy blanco y refleja muy bien la luz, probablemente vayas a ver muy bien el reflejo de esas bandas espectrales del Sol. Pero también hoy en día se trabaja en infrarrojo y eso también te permite ver otro tipo de señales sin esa contaminación tan grande de la luz del Sol, de la luz visible en este caso.
Podría, ya yendo a preguntas un poco más generales, que nos estamos acercando, quedan 12 minutitos, bueno, 14 minutos, nuestro contador va un poco adelantado para tener tiempo por si acaso. ¿Sería posible que Dart partiese a la mitad del asteroide o no?
Todo puede pasar, pero me resulta muy difícil imaginarme que eso pueda ocurrir, pero bueno, uno tiene que estar abierto a todas las posibilidades. No lo sé, la verdad es que no tengo ni idea de las probabilidades, pero bueno, tenemos que pensar que es un cuerpo muy pequeño, aunque vaya muy rápido, contra un cuerpo de 170 metros. Es decir, es un tal. Otra cosa es que sea un asteroide de pila de rubios y nos encontremos con un problema, ¿no? Que pueda atravesarlo. Pero bueno, lo dudo. Ahora mismo yo creo que esos cuerpos también absorben muy bien los impactos. Ya he dicho al principio que tenemos que estar abiertos a sorpresas, ¿no? A lo largo de la misión. Pero bueno, por posibilidad, ¿por qué no?
Según Christian, una herramienta interesante para llevar en una futura misión sería un oloroscopo para saber cómo huele. ¿Oloroscopio?
Bueno,
Para saber
al
cómo
horoscopio,
huele.
sí. Eso es muy de Futurama, esa referencia. Bueno, si al final hacemos oloroscopia nosotros, pero en este caso con los espectros, ¿no? De luz visible, de infrarrojos, lo hacemos de una manera bastante habitual. Entonces no hace falta olerlo en el sentido más extremo, pero bueno, ¿cómo podríamos olerlo? Pues bueno, con los espectrómetros de masas, por ejemplo, que ha llevado algunas misiones, por ejemplo, a la superficie de Marte, metiendo las rocas, haciéndole mil perrerías, cociéndolas, en fin, sometiéndolas a muchas pruebas y viendo qué gases salen, ¿no? Bueno, pues lo que pasa es que con un asteroide es mucho más difícil eso. Más que nada porque, bueno, vemos el requisito energético que necesita uno para llegar a un asteroide y posarse sobre su superficie, y además no puede frenar con nada, o sea que cuesta muchísimo.
Mencionar para el chat, esta misión no lleva ninguna ojiva nuclear, tranquilos, es una misión que es un impactador cinético, y también mencionar que cuando hablamos de cambiar la órbita, cambiar el rumbo, a lo que nos estamos refiriendo es que la luna que orbita a Didymos, está Didymos, que es el cuerpo más grande, y Dimorphos, que es la luna que lo orbita. Pues esa luna lo que se va a buscar es reducir su periodo orbital, que es alrededor de 12 horas, un poquito menos, se quiere reducir entre 1 minuto y medio, más o menos, 73 segundos, y 12 minutos. Entonces, realmente la órbita sí va a cambiar, la órbita general del sistema va a cambiar, pero no va a alterar de manera significativa todos los asteroides que hay alrededor, y realmente el cambio es tan minúsculo que no tiene sentido casi pensar que en un futuro va a desviar un asteroide y va a ir hacia la Tierra. Y en el hipotético caso de que pasase, pues habría un pequeño conflicto internacional.
Bueno, eso no. Con el baremo que se tiene de masas, de velocidades y de energías, eso no pasa, eso no debe de pasar, ¿no? Entonces,
solo puede pasar en la teoría.
Solamente puede pasar la teoría.
Para los teóricos sí puede pasar.
Y en las películas de Bruce Willis, pero bueno, en este momento no estamos en una película
pero Bruce Willis ha aprobado la misión. Bruce Willis approves.
Ah, bueno, pues entonces, adelante.
Entonces no tenemos problemas.
Bueno, estamos ahora mismo a algo más de 3.600 kilómetros de Dimorphos, ¿eh? Yo no digo nada.
Eso igual es el tamaño de Chile. Que Chile es un país muy largo.
Pues estoy ahora mismo, ya queda muy poco, estamos a 10 minutos, ¿eh?
Rolando, que estás por ahí, que es nuestro moderador de Chile. ¿Chile cuánto mide? ¿Te suena un tal Harry Stamper? Y si es importante para la misión, no me suena. Pero igual es alguna... Harry Stamper,
¿A mí?
sí.
Pues no, pero yo es que tengo muy mala memoria para los nombres.
No, pero que igual es un asesor científico de la NASA o algo, como...
A ver, Harry Stamper es Bruce Willis en Armageddon. O sea, con eso te lo digo todo.
LOL, vale.
Sí.
Vale.
Es el nombre de su personaje.
Vale. No he pillado la referencia. ¿De qué año es esa película?
1998.
Todavía no había nacido.
Pues fíjate.
No, o sea,
¿qué quieres acordarte?
La he visto, pero yo pensé que era más nueva, no sé.
Bueno, estamos ya debajo de la frontera de los 10 minutos, ¿eh?
Sí, ya, gente, podéis estar viendo en pantalla perfectamente dos puntitos, uno grande, uno más pequeño. Nosotros vamos a intentar, bueno, la sonda DART, yo no, va a intentar impactar en la luna más pequeña de todas.
Vamos a ver qué qué ocurre, porque bueno, ya queda realmente poco. Esto es emocionante ver estos últimos minutos.
Por aquí han dicho que Chile mide más de 4.000 kilómetros.
Bueno, pues entonces realmente
Está más
sí.
cerca de Dimorphos que Tierra del Fuego de la parte más al norte.
Así es. Ahora mismo vamos a ver qué hora es, la 1:06:36. Estamos aproximadamente a 2.800 kilómetros de Didymos. Ya empezamos a ver algo más.
Sí, esperemos.
Vamos a ver qué ocurre. Y vamos a ver bueno, ahí estamos a ver el momento clave.
Bueno, al final es una misión que se resume en pocos segundos, en un momento muy concreto. Se sabe si ya, si ha impactado o no, y eso ya, que impacte ya al menos dice, bueno, parte de la tecnología funciona.
Claro, lo importante al final va a ser en cierta manera que obviamente la nave puede autonavegar por sí misma, ¿no? Es una cosa bastante compleja, es un entorno pues, bastante hostil para una navegación, aunque como podemos ver en las imágenes no hay ninguna estrella ni se ve nada de fondo, afortunadamente que pueda confundir a Dart,
Bueno,
pero bueno, que
eso es
es
bastante
difícil.
fácil de evitar, ¿eh? Eso es bastante fácil de evitar.
Bueno, depende de lo oscuro que sea el asteroide. Si tuviera un albedo bajo, no sé si se podría hacer tan bien ni tan fácilmente.
Puede ser.
Entonces, bueno, vamos a ver qué tal. Bueno, acaba la cosa. Ya quedan 6 minutos 47 segundos. Me sale a mí.
Voy a poner ahora en el directo una descripción gráfica de la misión. No sé si la has visto.
Pues no lo sé, porque tengo solamente el directo de la NASA.
No,
Estamos ahora.
el tweet que hemos puesto de descripción gráfica de la misión.
No lo he visto.
Bueno, ahora.
2.000 kilómetros quedan.
2.000 kilómetros, eso es menos que de Barcelona a Canarias. Gente, de manera rápida, descripción de la misión. Lo que va a suceder es algo así. Un satélite muy pequeño se va a estampar contra una luna muy grande y no le va a hacer nada. Pero la va a mover un poquito y le va a cambiar un poquito su órbita.
Algo así, sí. Algo así, vamos a ver. Ya queda, joder, es que queda tan poco. Estamos viendo ya Dimorphos bastante bien, ¿eh?
Sí, ya se ve bien, ya se ve bien. Voy a hacer esto, voy a hacer nuestros caretos más pequeños.
No sé si Didymos tiene la forma tan parecida a lo que sabíamos de la curva de luz, pero Dimorphos me está sorprendiendo que es el pequeño, que sí que parece bastante ovalado con respecto, bueno, por lo menos así en estas imágenes, con respecto a lo que estábamos viendo en los datos que teníamos o en el modelo de forma que había salido de la curva de luz y de las imágenes de radar, ¿no? Ahora cuando digo que RIP Arecibo, qué pena que el radiotelescopio de Arecibo se rompiese.
Cierto.
Pero bueno.
Cosas que pasan. Además, acabó de una manera muy triste.
Sí, acabó pues con el pésimo mantenimiento. Al final las cosas pues se rompen, ¿no? Y dejan de funcionar. Madre mía, quedan 4 minutos, por Dios.
¿Qué 4 minutos?
A ver, son las 1:10, a ver, 23, que tengo aquí, es que como lo tengo en una tabla de Excel, los kilómetros, a ver. Pues ahora mismo quedan 1.481 kilómetros.
Ahora mismo la NASA se encuentra en el Final Come Opportunity. Este es el momento último de la NASA para hacer cualquier cosa a partir de este momento, que justo ahora acaba de pasar. La NASA ya no tiene absolutamente nada de control sobre la sonda y bueno, que todo vaya bien.
Sí. Vamos a ver.
Justo he puesto de fondo el... Los ingenieros de la NASA ya están mirando diciendo, ¿está todo el pescado vendido?
Sí, ahora pase lo que pase, ya no se puede hacer nada. Bueno, tampoco sé cuánto se podría hacer antes, ¿no? Porque el cambio de velocidad, pero bueno, ya va muy bien dirigido, afortunadamente. Ayer creo que se conocía la posición con una incertidumbre de 2 kilómetros. Eso es muy bien, ¿no? Eso es una incertidumbre muy baja, teniendo en cuenta el pequeño tamaño, las dificultades para observar el asteroide resuelto, o en este caso ver a Dimorphos bien resuelto. O sea que muy bien, muy bien.
Por aquí lo mencionan y es cierto, la nave no va para nada lenta, va muy rápido. De hecho, a 6 con algo kilómetros por segundo, 24.000 kilómetros por hora. O sea, va muy rápido, lo que pasa es que son, como estamos diciendo, distancias muy elevadas.
Bueno, ahora mismo quedan 800 kilómetros, 850 kilómetros, me sale a mí. O sea que está muy cerca ahora mismo. Lo que pasa es que estamos viendo con un poco de retraso las
imágenes.
Las imágenes, ¿no? Porque obviamente tiene que llegar hasta la Tierra, hay un tiempo tal, pero bueno, que está ahí ya. El impacto va a ocurrir en 2 minutos.
Sí. Por aquí preguntan si las imágenes son reales o de Nintendo 64. Son reales y madre mía el más grande, Didymos.
Increíble.
Sí. Dios, qué detalle. Y tiene centradísimo, ¿eh?
Sí, ahora sí está muy centrado ya.
Hay todos los telescopios de la Tierra que pueden apuntando. No se va a ver a simple vista, ¿eh? Si alguien se lo pregunta, que bueno, lo he leído que se lo preguntaba.
1:13, madre mía, 1:13:09, vamos a ver cuánto.
Ay.
Está a 451 kilómetros.
Claro, 1:13 quiere decir que en breve. 1:14 era la hora del impacto o la hora que nos llegaba la señal del impacto.
Es la hora del impacto.
Entonces nos llega a 1:15.
Sí, aproximadamente tiene que llegar más o menos. Sí. Quedan 2 minutos en 41 segundos en la imagen.
Pues 15 segundos en la realidad.
Madre mía, qué nervios.
Madre mía. Estoy nerviosísimo, o sea. Pero lo que me gusta es que lo estoy viendo centrado. Y las imágenes que se han visto de la izquierda de Didymos, muy buena calidad. O sea, me sorprende.
Sí, está siendo maravilloso. Bueno, yo creo que ella en 10 segundos o 15 debería de haber chocado ya, ¿eh?
Sí, de hecho ya son justo y 14. En estos momentos ya tiene que haber chocado. Y por aquí dicen que va a la misma velocidad que el coche de Fernando Alonso. No será el Alpine, igual será otro. ¿A cuántos kilómetros va la sonda? Si es kilómetros por hora, 24.000. Una velocidad muy alta que seguro que te ponen multa por la autopista. Efectivamente, estas cosas no suceden todos los días. Este es un evento histórico. Y cada vez se está viendo con más resolución Dimorphos y sigue muy centrado, ¿eh? Yo creo que Diana en el centro. Tenéis una encuesta que solo el 22% de momento ha dicho que va a haber Diana en el centro.
Vamos a ver, ya está muy cerquita, madre mía.
Toma nota, que luego nos tienes que decir más o menos qué tipo de imágenes crees que son. O sea, qué tipo de composición tienen. ¡Dios! Sí. Esta es la última, esta. Hostia,
no, todavía quedan.
Hostia. Ya está.
La última yo creo que hay 17, o sea, todavía igual queda un poco, ¿o no?
Mira qué calidad.
Sí. Ay, sí que Rubel, parece que sí que es una pila de rubies, sí.
¡Wow! ¡Qué
Increíble.
épico! ¡Qué épico! Esto, gente, es muy épico lo que ha conseguido la NASA, impactar con una sonda tan pequeña en un punto tan alejado a una velocidad tan rápido en todo el centro. Ha sido todo un logro.
Espectacular.
Mira,
espectacular.
ahí está el jefe de programas científicos de la NASA, el que va de traje, que de hecho acaba su cargo en el mes de diciembre. Uf, Zubben,
Ya
o algo
está,
así.
ya, Zurbuche, ya ha tocado su sitio.
Si recordad que os podéis suscribir al canal de Frontera, tenéis un vídeo donde también explicamos todos los detalles y los detalles más importantes de esta misión, datos curiosos, está subido y como siempre todas las semanas hay novedades, así que os podéis suscribir a Frontera y seguirnos en Twitter, que están los links en la descripción. Y también Geólogo en Apuros, que lo lleváis viendo todo el ratito al lado de su foto, pues lo buscáis en Twitter y también hace muy buen contenido. Qué gran momento, ¿eh?
Increíble.
¿Qué nos puedes decir a partir de las rocas que has visto?
Bueno, yo creo que por lo que se ve en las imágenes, me imagino que bueno, tendremos luego un mejor nivel de detalle cuando la suban. Sí que parece un asteroide muy similar, si os fijáis, a Venus, Ryugu. Parece una pila de rubios.
Me ha parecido parecido, sí.
Sí. O sea que bueno, parece en ese sentido sí que parece un asteroide muy similar. Es cierto que la densidad de Didymos es de unos 3 gramos por centímetro cúbico, que es lo que esperamos de una roca, de un asteroide de tipo S, ¿no? Pero sin embargo Didymos tiene apariencia de estar más fragmentado, por lo menos en estas imágenes, ¿no? Vamos a ver cuando las tengamos todas, si son parecidos, si son muy diferentes o cómo son. Pero desde luego parece una pila de rubios, ¿eh?
Sí, o sea, muy buena calidad. Eso también, a partir de eso que dices, ¿crees que habrá mucho o poco cambio de órbita? O sea, ¿crees que habrá absorbido mucho impacto o que no y que el cambio de órbita va a ser más...?
Yo creo que va a haber cierto cambio de órbita porque al no ser monolítico es posible que haya salido bastante material eyectado. O sea que aún así vamos a ver, dependiendo también de la distribución de las rocas del interior, si son más gruesas o más finas y de la cantidad de regolito y tal, pero yo creo que sí que va a haber un cambio evidente en la órbita.
Mencionar que todavía no... O sea, no lo hemos comentado y los cambios de la desviación todavía no lo vamos a saber, lo vamos a saber a partir de dentro de unas semanas y luego durante 2 o 3 meses se va a estar comprobando y se va a estar afinando ese cálculo. De hecho, seguro que habrá gente que mañana saca papers diciendo a partir de las observaciones que tal, el cambio es este. Luego en la revisión por pares lo cambiarán.
Claro.
Y ajustarán, pero bueno, lo que le pasa a muchos es que quieren sacar el paper antes que nadie. Solo era empujarla, pero no destruirla, efectivamente. Solo era empujar y no destruir.
Claro, es alucinante.
¿Qué sensación se te ha quedado después de ver eso? De cómo se iba acercando cada vez más cerca hasta que...
Bueno, yo creo que de algún modo mucha alegría, ¿no? Porque estamos viendo pues una misión histórica que ha funcionado a la primera, que a veces es muy difícil, ¿no? Y yo creo que bueno, esto es una primera vez de una primera misión de defensa planetaria que ha funcionado a la primera y bueno, creo que eso es muy importante, ¿no? Yo creo que es un éxito total de la NASA. Y bueno, vamos a ver qué podemos aprender en los días siguientes, ¿no? Vamos a esperar a que nos suban las imágenes de alta calidad. Y bueno, para poder trastearlas con ellas y ver qué podemos aprender también, ¿no?
¿Tú estás enfocado, que no te lo he preguntado antes, en este tipo de estudios o no?
Yo no, yo me dedico ahora a la docencia y a la divulgación, no me dedico a la geología pura y dura.
No digo, igual en sus tiempos libres sí que se dedicaba a alguna cosilla. Bueno.
No. Bueno, me dedico pero a diseñar instrumentación, no a
bueno. Vale.
No a otra cosa. O sea que, pero bueno, que esto sí, la geología planetaria siempre la sigo.
Pero que los papers habrá que leerlos.
Sí, hombre, vamos a ver, paper, mira, ahí está Bill Nye, el hombre de la ciencia, ahí
Cierto.
echándose un selfie. Y bueno, vamos a ver qué nos cuentan, ¿no? Vamos a ver paper seguramente durante meses, en conferencias ahora en otoño. Bueno, vamos a ver, yo creo que vamos a ver muchas
Sí, sí,
cosas.
sí. Y porque justo el IACA acaba de ser, si no, también seguro que habría algo interesante en... Igual hasta en el IAC del año que viene hay cosas interesantes de esta misión.
Segurísimo porque...
Sí, sí, segurísimo porque está Italia participando y el año que viene es en Milán.
Eso, además, nos quedan las observaciones terrestres, las del J-Web, nos quedan un montón de cosas que tendrán que unirse todos esos datos, saldrán simulaciones, en fin. Yo creo que va a ser muy una época o un año muy intenso, ¿no? En cuanto a paper y a descubrimientos de los que se van a poder hacer.
Repetimos que el desvío no lo vamos a saber ahora, lo vamos a saber dentro de 2-3 semanas, cuando ya se hayan hecho las primeras mediciones, se hayan más o menos comprobado. ¿Por qué? Porque en estos momentos sí es cierto que los telescopios, muchos telescopios de la Tierra han estado observando el evento, pero eso no quiere decir que te vayan a sacar los resultados al momento.
Claro, eso es imposible, ¿no? Tenemos que... La ciencia a veces necesita también un poco de reposo. Esto es como la cocina, ¿no? Hay que esperar todavía. Veremos en un tiempo cuando se procesen las curvas de luz y bueno, todo lo que se tiene que hacer para ver si realmente ha habido un adelanto, un retraso del tiempo del periodo orbital de Didymos.
Sí,
De Dimorphos, perdón.
Dimorphos. Recordemos que es una variación de órbita muy pequeña, de entre 73 segundos y 12 minutos. ¿Podrías así tirarte un triple a partir del material? Decir, yo creo que...
No tengo ni idea porque la horquilla que manejaban
Sí,
los científicos era
eso entre
72 segundos y no sé cuántos minutos, no sé, 10 minutos.
73 segundos y 12 minutos.
Y 12 minutos.
Bueno,
yo, la verdad es que no tengo ni idea. Yo voy a esperar a que lo calculen ellos porque seguro que si digo yo va a ser al revés.
Bueno, esto es como cuando decíamos que la Starship iba a volar en noviembre, diciembre del 2021.
Bueno, ha llovido mucho.
O el SLS o el James Webb.
Sí.
Todo cambia. Puedes decir algo que al final va a cambiar. Por aquí dicen que podían haber pedido ayuda a Superman. También era otra opción, pero creo que estaba de vacaciones estos días.
Sí, yo creo que también estaba de vacaciones, ¿eh? Al final, yo creo que más que de vacaciones, yo creo que ha fallado un poco el tema de también un poco más de publicidad, un poco más de que la NASA hubiese sido un poco más machacona. Igual que ha sido con el SLS, que ha sido bastante machacona. A lo mejor con la DART también tendría que haber dado un poco más de caña, ¿no?
Pero igual ha estado ocupado este verano y es una de estas personas que se coge las vacaciones a final de septiembre, que están más baratos los hoteles y tal. Igual por eso, por eso no estaba disponible.
Podría ser.
No me hables del SLS.
No, bueno, ya con eso tenemos todos un poco de disgusto.
Reímos por no llorar.
Bueno, la NASA tiene, yo no sé si es un problema o es una ventaja. Es decir, el hecho de acertar a la primera, de construir un cohete como el SLS y una misión entera sin haber hecho ninguna prueba, bueno, vamos a ver si las pruebas en tierra, tal.
Sí. No,
pero no como SpaceX que tú vas viendo que hay un prototipo y va cambiando, no. A la primera, a mí eso me parece muy fuerte.
Pero a veces la NASA tiene una tontería encima que no se la quita, como estos días. Tenías una tormenta tropical que amenazaba, que todas las predicciones decían que iba a pasar por Florida, que iba a pasar por Cabo Cañaveral. La NASA, me espero. Hasta que no han declarado que es un huracán, no han dicho que hay que guardar el SLS en el hangar.
Sí, es un poco, no sé si llamarlo quizá agonía, ¿no?
Sí,
la decisión.
Puede ser, pero no sé, estaba bastante claro. No sé.
Claro.
O sea, nos la hemos jugado tanto con ese cohete no se puede romper, y menos por un huracán por haber tomado una mala decisión como esta.
Efectivamente, no se puede entender así, ¿no? Vamos a ver, yo tengo confianza de que el SLS a la siguiente, en 6 de noviembre, por lo menos despegue, ¿no?
Esperemos.
Vamos a ver qué tal pasa.
Pues iría acabando por aquí el directo, ¿eh? Que es
Bueno, pues
es tardecito y mañana hay clase.
sí, ya es tarde. Mañana más, ¿no?
Sí, mañana, bueno,
Bueno.
a analizar las imágenes que nos saquen.
Sí, pues sobre todo yo espero ya las delicias Cube. No sé
Sí,
cuál
sí.
será la política que va a tener la Agencia Espacial Italiana con respecto a esas imágenes, pero yo creo que también van a ser... Bueno, vamos a ver, se me olvidaba, que nadie se piense que las imágenes de Delicia Cube bajaban a la velocidad de DART.
No,
Las
no.
imágenes de Delicia Cube, por desgracia, son un satélite muy pequeño, tiene una antena muy pequeña y seguramente tarden bastante en descargarse. Es decir, me imagino que si la política de imágenes es positiva, iremos viendo un chorreo de imágenes a lo largo del tiempo, pero que nadie se piense que va a haber toda la secuencia de golpe porque va a ser, me da la impresión de que va a ser muy difícil.
Sí, también no sé si lo he mencionado, creo que sí a lo largo del directo. En estos momentos DART tenía concentradas 2 antenas desde Canberra, que de hecho ya sale que no están recibiendo señal. Tenía la antena más grande del Deep Space Network de Australia y y otra antena también de Australia. Y es que eran imágenes que o las pescas al vuelo o las pierdes. Entonces, toda la capacidad se estaba centrando en recoger lo que me va a enviar DART. LiceaCube me lo puede enviar tranquilamente a partir de ahora o a partir de dentro de una hora, depende cómo estén las posiciones. Que por cierto, justo ahora la antena 54 de Madrid se está comunicando con el James Webb.
Claro, porque el J-Webb va a hacer una secuencia de 5 horas de observación desde antes hasta el final, ¿no?
También muy
es importante.
interesante saber lo que saque el James Webb.
Claro, yo creo, no sé, va a ser con NIRCam, no sé en qué modo va a hacerlo, veremos a ver cuál es el resultado, ¿no? Sea cual sea, yo creo que va a ser siempre lo digo, siempre va a ser positivo porque el J-Webb todavía no tiene muchísimo que aportar y yo creo que también va a ser un poco revolucionario para estas cosas, ¿no? Estos días también va a estudiar Chariclo, estos días, el J-Webb. Va a hacer bastantes cosas así de asteroides, o sea que vamos a ver con qué nos sorprende las próximas semanas.
Sí, estará ocupado. Bueno, pues no te entretengo más, que es eso, que es tarde. Y bueno, a todos vosotros recordad que nos podéis seguir a Frontera Espacial. Esta noche vamos a estar poniendo contenido, o sea, Frontera Espacial no para, siempre está poniendo contenido. Pero eso, nos podéis seguir en Twitter, el link en la descripción, aquí en YouTube, que ponemos muchos vídeos. Hay un resumen semanal cada semana sobre toda la actualidad espacial. Y luego a Geólogo en Apuros en Twitter lo podéis buscar, que lo encontraréis fácil. Y si miráis en algunos de nuestros tweets, le estamos haciendo ping, así que le podéis encontrar fácil. Muchas gracias por pasarte.
Pues nada, muchas gracias por contar conmigo. Y una cosa antes de irme, acaban de llegar los fotogramas del último vuelo del Ingenuity.
No
ahora mismo, hace 8 minutos.
Ingenuity,
Sí,
que no quiere perder protagonismo. Espera, ¿dónde está? Claro, ahora todo el mundo está hablando de lo mismo, o sea, a nadie le interesa Ingenuity. JPL, ¿no? ¿Lo habrá enviado?
No, lo tengo en mi bot acaba de decirlo.
Ah, vale.
Te mando el enlace por Twitter, acaban de salir ahora
guay. Sí.
los fotogramas.
Ah, vale, que han salido, vale, no han puesto el tweet.
No han puesto el tweet,
vale.
pero han llegado 73 fotogramas en blanco y negro y uno en color.
Uno en
o sea
color.
Que uno en color, sí.
Bueno, pues ahora me lo pasas y pondremos algo en Twitter esta noche. No solo ponemos cosas de DART. Muchas gracias a todos por acompañarnos y nos vemos muy pronto en otro directo. Hasta luego, gente.
Hasta luego, adiós.
Vale, ya está, ya no.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Liftoff.